First and foremost, I extend a warm welcome to each one of you at the IZTECH event hosted by İzmir Institute of Technology, with contributions from Optica, IEEE Photonics Society, and the İZTECH Optics and Photonics Society and Department of Photonics. My name is Özuğur, and I'm a first-year student in the Photonics department. It's a great pleasure to be among you for this significant event. Now, I would like to turn the virtual stage over to Professor Canan Varlıklı, our department chair and advisor, who has played a significant role in making this event possible. I invite her to deliver the opening speech.
So, good morning, all. And thank you very much, Ilgin, for that great introduction. My respectful and dear rector, Professor Dr. Yusuf Baran, dear colleagues, and our precious students. It is with great pleasure that we, the İzmir Institute of Technology Photonics family, welcome you to this year's World Day of Photonics event. Our primary goal in organizing the annual talks on Photonics Science and Technologies with our precious students is to increase awareness, foster collaboration, share knowledge, and address the current challenges and opportunities in the field of photonics. I believe it is hard for you to imagine how joyful it is for me and also for the faculty members of our Department of Photonics in 2019, the year that we met our first undergrad students to have the center set. I remember the excitement and also the anxiety we felt in 2019 when our first undergrad students arrived in the Department of Photonics. I would like to share a memory with you. That year, only a few months before the arrival of our first undergrad students, I received a call from the security of our institute at the entrance gate saying, "Dear professor, there is a company here saying that they're going to install an instrument in your research laboratory, and they're asking where the Photonics department is." So in 2019, together with those bright young minds who enrolled in our undergrad program to become photonists, light scientists, and engineers, we launched the Light Point late light meetings, started celebrating the Day of Light during the pandemic conditions, established student communities as the members of international organizations, answered thousands of questions of what is photonics, and erased, well, let's be honest, significantly erased the number of the words like photonics, photogenics, photonics. So this year we are holding the third celebration of Day of Photonics. The first was in 2022. Although most of those involved in the organization are currently in a mathematics exam, I can kindly invite you to applaud those bright young people for their dedication, faith, and hard work. As long as they and others like them are around, there is hope. So please. So now I have the privilege to say the IZTECH Department of Photonics, IZTECH Optics and Photonics, and IEEE Photonics Society student chapters have come together to organize IZPHOTECH in celebration of the World Day of Photonics with contributions from the IEEE Photonics Society Türkiye chapter, Optica, Optics, Teknotip, and our dear career development course lecturer, Ebru Aslan Çallıoğlu. The breaks that are offered in the lobby are from our career lecturer. On behalf of the organizing committee, I would like to extend my heartfelt thanks to all of them. Our celebration of Day of Photonics, IZPHOTECH 24, has taken more than 200 registrations all around the world, including the countries of India, Uzbekistan, United States of America, and of course our great country, Turkey. So 17 different organizations has registered. Throughout IZPHOTECH 24, we will have the opportunity to listen to and engage 13 scientific talks that highlight contributions to photonic technologies in the fields such as biophotonics, communications, lasers, solar energy, and security. 8 of these presentations will be delivered in person. I would like to thank all our speakers for dedicating their invaluable time and expertise to this event. This year, for the first time, we are also excited to showcase 20 poster presentations to support the enthusiasm of our young photonists, light scientists, and engineers. I hope that these valuable speeches and presentations, of all which will be streamed and archived in the official YouTube channel of IZTECH Optics and Photonics Student Chapter, will inspire many photonic enthusiasts and foster the collaboration. So let's appreciate the importance of photonics in our lives. Thank you.
Before we move forward, I extend my sincere thanks to Professor Canan Varlıklı for gracing us with her presence and for her instrumental role in bringing this event to life. Her dedication and leadership have truly set the tone for what promises to be an enlightening and inspiring occasion. Now, it's my honor to welcome to the stage our esteemed Rector, Yusuf Baran. His unwavering support for academic endeavors and commitment to fostering an environment of innovation and knowledge sharing have been pivotal. I invite Rector Yusuf Baran to address our distinguished audience and officially inaugurate the IZPHOTECH event. Thank you.
Good morning, everyone, distinguished speakers, dear students, dear colleagues. It's a real pleasure for me to be here and to be in the opening session of IZPHOTECH. And it's a real honor for IZTECH, for all of us, to be the first university having photonics department for Bachelor of Science education in Turkey, and also having master and PhD programs for photonics at IZTECH. So we were #1 in Turkey, establishing this department at bachelor, then master and PhD levels. And then we are happy to see that we are copy and pasted by the other universities. Then the second and the third photonics departments were established. And we all know that, disciplines are disappearing and they are newly born. And one of the very recently born discipline is photonics. And of course, it's quite interdisciplinary approach regarding with the light science and engineering. And when we first time established this department, I remember very well from the other universities, people were asking about this department, and even for the students taking the national university exam. And when you look at the ranking of preference of national university exam taking students, you can very easily see that IZTECH Photonics department is, going up quite significantly. And even in last 1 year, the ranking was 43,000 more than the previous year. And when you look at the commitment and when you look at the contribution of our departments to society, you can easily see that photonics department first, of course, develop the current and the future leaders for photonics discipline. And when you look at our alumni, you can very easily see that they are doing great in different industrial positions or the university positions in Turkey or in abroad as well. And of course, they are going to be like stars that will be followed by the following students. And of course, they will try their best to achieve more and more. And of course, we contribute to society as well. And in nanotechnology, biotechnology, life sciences, security, communication or defense disciplines, you can very easily see the effect of photonics on development of these areas. And photonics students community, I follow them very well, and they are achieving very good, and they are doing great as well. And every year they organize different online or face-to-face meetings, and even these activities increase the visibility of our university, our department, and this discipline as well, because we need to increase the awareness of photonics and its importance in our society as well. My sincere thanks go to all the participants, and especially to invited speakers for coming and joining us, and for the invited speakers to share their knowledge and experience with our students, Bachelor of Science or Master and PhD students. And these knowledge transfer will increase the amount of the information that we generate in our university and for the development of our students as well. And one more thanks will go to all the sponsors for their support to realize this event happen. And of course, I want to thank to Professor Dr. Canan Varlıklı for her commitment, dedication, and the leadership. And of course, our student club, Photonics Student Club, for organizing this event. One of the key issues in our life is the sustainability. It doesn't matter whether you do something for the first time, but it has to be sustainable. It has to be continuous. And I am very happy to see that our Photonics Student Club is quite sustainable with its activities and with the memberships. And it's also very nice to see that Photonics Student Club community is composed of from different students from different departments as well, which provides a multidisciplinary or even antidisciplinary approach to talk about any problem or to find any solution. Once again, I want to thank all the participants for their commitment and support, and I wish you a fruitful meeting. Thank you.
I extend two sincere thanks to our Rector Yusuf Baran. It's my great pleasure to introduce Dr. Martin Byrdin, a renowned researcher and expert in biophysics and structural biology. Dr. Byrdin earned his master's degree in biophysics from Moscow State University in 1994, followed by a PhD in physics from Free University Berlin in 1999. Since 2004, he has been a dedicated researcher at the French Atomic Energy Commission, first in Saclay and later at the Institute for Structural Biology in Grenoble. Currently, Dr. Byrdin serves as research director at CEA Grenoble, where he focuses on photoactivatable bio-nano engines, particularly proteins. His work pushes the boundaries of optical spectroscopies to unravel to complex structures, dynamics, and functions of these bio-nano systems. Please join me in welcoming Dr. Martin Byrdin, who will be sharing his insights on the impact of triplet-stage population on GFP-type fluorescence and photobleaching.
I'm sure you understand the thing to do is biophotonics, because it deals with living matter and technology at the same time. I'm especially honored to have been assigned this opening slot when everybody is wide awake and attentive. So let's dedicate this first hour to biophotonics. I come from Grenoble, as you heard. It's in the French Alps, and people used to come there for doing skiing. And in 1968, there even was a Olympic Winter Games in Grenoble, but by now most of the glaciers are gone, and it's so the highest photon flux research reactor that can be used for structural studies of proteins as well. It's not by chance that this building is the Institute for Structural Biology. It has been built next to the synchrotron and the reactor in order to use these instruments for structural biology. People in the institute study mostly structures of proteins, but not only, they also study function of proteins and the dynamics. And this is where a spectroscopist, as myself, can find his place in an Institute for Structural Biology, because you will learn that spectroscopy can contribute a great deal to understanding function of proteins, hopefully. So this is the outline. I will speak about a protein. This protein is called green fluorescent protein, or GFP, as was in the title. But before that, I'll shortly give some historical background. Then I'll speak about the amazing photochemistry of GFP. And in the conclusions, I'll give you the take-home message in one sentence, and that is that GFP photon budget is not energy independent. Hopefully, in an hour from now, you will be able to appreciate the importance of this sentence. For those who are in the audience physically, it's your privilege. This is Thomas Hirschfeld, German Jew, raised in Uruguay, worked in America, in the States, and was dead long before most of you were born. But it's anyway a name you might want to remember. The guy had over 100 patents, and he's the person who invented the fax machine, invented and built the first fax machine. Fax being fluorescence activated cell sorting. Oops, too fast. This one. And it consists in sorting living cells into two pots, into one pot or another pot, depending on whether they carry or not a fluorescence label. So imagine those living cells, they have the size of few microns, and they fly past the detector in few milliseconds. So if you want to detect a fluorescent signal in few milliseconds of a particle as small as few microns, you need to attach a tag that is really, really, really fluorescent. So he would not settle for anything less than the best one, and that was fluorescein. It's actually one of the best fluorophores known. Has absorption of almost 100,000, and the fluorescence quantum yield is 0.9. Provided you are in alkaline solution at high pH, then this H goes away and this molecule starts to fluoresce like hell. But what do you need in order to have such a good fluorescence? First of all, you need a band gap in the visible between the highest occupied and the lowest unoccupied molecular orbital. Second, you need a decent overlay between the wave functions of those two states, because that overlap integral will determine the absorption cross-section. Here I call it epsilon in a macroscopic level, and a microscopic level it's a cross-section sigma. And it will also determine the radiative rate constant K. That is the measure for the fluorescence. So basically, a good emitter is always a good absorber. But that's not all you need, because in order to observe fluorescence, you need to excite it. So the observable excitation rate is the product of the incoming photon flux with the absorption cross-section, which I put here as sigma. This is an observable excitation rate. How many fluorophores you excite per second? On the emission side, you also have to modify the radiant rate constant by the probability that the molecule, the excited molecule, will undergo this pass. So you multiply the rate constant, the intrinsic rate constant, by the quantum yield of the fluorescence, which is the probability that you take this pass and not any of the possible other passes of non-radiative deactivation. That could be anything like internal conversion, isomerization, or quenching by the environment. All of those have in common that the energy of the excited state is not emitted as radiation, but it's lost as heat to the solvent. So this can happen, this will happen, and therefore the probability to take this path is not 1, and you have to multiply the radiative rate constant with the fluorescent quantum yield, which is just the fraction you can see. Now, with this preparation, we can determine the rate of the fluorescence emitted as the number of photons coming in multiplied by the 2 factors that govern the outcome, and this is the emission coefficient, the extinction coefficient, and the emission yield. So the product of the 2 is called the brightness of a fluorophore, and this brightness is the proportional constant, proportionality constant between the fluorescence output and the incoming photon flux. So it's not a surprise now that the fluorescence rate is proportional to the energy coming in and to this brightness. It is maybe more unexpected that there's another thing which scales linearly with the incoming energy and the brightness, and that is the photobleaching. No fluorophore lives forever. Every fluorophore in the excited state can undergo photochemistry. It can take an electron, can leave an electron, can take a proton, leave a proton. All those processes, if they are reversible, they will count like quenching. But if they're irreversible, you will lose the chromophore. It will not fluoresce anymore, and therefore, over time, the fluorescence intensity will go down. And this bleaching with a yield of PC, like photobleaching, also scales with the brightness, because it's the brightness that determines the speed with which the chromophore cycles between the ground and the excited state. So this is the second thing, which is a little unexpected, that the photobleaching is high for the brightest chromophore. The brighter the chromophore, the faster the photobleaching. And that is actually what was found by Hirschfeld when he studied the fluorescein molecule. He found that both the emission rate and the bleaching rate scale with the excitation energy. But, and now comes another interesting result he found, the area under the curve, which is the product of the amplitude and the decay time, is independent of excitation energy. It's independent of brightness. It's only depending on the fluorescence quantum yield and the bleaching quantum yield. Their ratio determines this photon budget of the molecule. Photon budget is how many photons the molecule can emit before it is irreversibly destroyed and lost. Now this is the law of Hirschfeld. And he not only did it derive it theoretically, he also tested it experimentally. And for fluorescein, it is valid. He quenched fluorescein with different quenchers, and he found if you quench the fluorescence, then the bleaching goes slower, but the amplitude is less again. So the product of the bleaching time and the emission rate will stay constant. That's Hirschfeld's law. And the question now is it applicable to GFP? And that's why we go to GFP, this amazing molecule, a gift of nature, I'd say. And I will never speak of green fluorescent protein anymore. I will use GFP. This is a small protein. It's 25 kilodalton in weight. Has the form of a barrel, a beta barrel, and the barrel holds in its middle a chromophore. This is the chemical structure of the chromophore. It's formed from 3 amino acids. This is tyrosine, and the 2 neighboring amino acids here and here, they form a second circle. So in the end, the chromophore moiety looks resemblance to fluorescein molecule. You have 3 cycles, 1, 2, and the third one is not complete, and that makes that this bridge is flexible. Especially in excited state, this bridge becomes very flexible, and this molecule in solution, once excited, isomerizes. It does not fluoresce at all. It has a fluorescence lifetime of few picoseconds. You don't see the fluorescence because it's de-excited by isomerization along this double bond. But inside the barrel, the protein, the chromophore is held fixed. It's much less flexible, and therefore it has a decent quantum yield of 0.6. And the absorption is 50,000. So together, it's about 1/3 of the brightness of fluorescein. It's really decent fluorescence. But the amazing thing about this molecule is not only it's nice, bright fluorescence. It is that it is a protein. So it has a gene that encodes the protein, and this gene you can attach it to the gene of any protein you want to see in a cell. As soon as the cell expresses the protein you want to see, it's bound to express this protein as well. And if you put the cell under the microscope, shine a laser on it, you see light up any of the proteins you want to see, which is completely impossible in any transmission microscopy because the proteins are too small to be seen. But if they light up, you have a bright spot on the microscope. So this is really a gift, but as any gift, it doesn't come without a price. The wild type version of this protein does not fluoresce a lot. And this is something interesting. It's like with the fluorescein protein, as long as this proton here is here, the fluorescence is weak. You need to remove the proton in order to have the strong fluorescence, but you cannot go with high pH here. This is a protein, it will denaturate. So what we do, we mutate 1 or 2 amino acids next to the proton so that they are more bulky and there's no space left for the proton. And this mutated protein, it's no longer GFP, it's eGFP. It's enhanced green fluorescent protein. And all we see here, this is enhanced green fluorescent protein. I will say GFP, but I mean eGFP. And in order to make the confusion complete, I put GFP type proteins in the title, because everything which has this barrel, this chromophore, and the mutation which prevents the H from being there will fluoresce brightly. But if you mutate a bit the chromophore itself, you can have different colors as well. But today we speak about the green ones, because they're the oldest ones and the brightest ones. So now you know what GFP is. And now let's do the Hirschfeld experiment. Take the protein, put it under a microscope, switch on the laser, and see how the fluorescence behaves. Oh, the fluorescence goes down. But if you remember the picture of the fluorescein molecule, the curve has not the same form, not the same shape. It's biphasic. You have a rapid phase and you have a slow phase. It is new. Might be due to who says biphasic, who says dirt. There might be something else in the cell, but I assure you it's not the case. This comes from a column, chromatographic column. It's homogeneous, so it's not a heterogeneous sample. It's a homogeneous sample. Might be something else heterogeneous. For instance, the illumination. If you have a laser beam which has Gaussian shape, it's intense in the middle and weak at the edges, then you would have rapid bleaching from the middle and slow bleaching from the edges. That's not our case. Our laser beam has top hat profile. You see, it's flat. And moreover, we detect only the central part of the excitation beam. So we detect this little fraction and it's really homogeneous. So the laser excitation is not, the excitation laser is not at the origin of the inhomogeneity either. Let's do another experiment. Let's put the protein in the microscope and observe absorbance instead of fluorescence. Same picture, fast phase, slow phase. Only the amplitude ratio is not the same as in the fluorescence experiment, but still you have this fast phase and the slow phase. Is that maybe due to the fact that we did not look at the same spot? Because proteins are living things, they might behave differently one from the other. As the question really difficult to answer, so we had to invest some time and money in thinking and doing and building a microscope which allows to observe fluorescence at the same time at the same spot. We call it kaleidoscope, and it actually looks like a microscope, but it's a spectrometer. So the sample is here, and it's situated between two objectives, one from the bottom, one from the top, and between the two you can do absorption measurements. And here are mirrors that separate the optical path into various optical passes. So you can send a laser in, you can send a lamp in, and you can couple a spectrometer which observes the absorption, and another spectrometer which observes the fluorescence. And then you can have both curves at the same time at the same spot. You make sure that there is no artifact due to the variance in the sample. This is what we get. We compare the two and we see the amplitude ratio for fluorescence decay and absorption decay is not the same. Meaning we have in that sample something which loses fluorescence but does not lose absorption. And now something interesting. I have no picture to show it, but if you switch off the light for a second, then this lost fluorescence comes back. So it's not lost permanently, it's lost temporarily. So this is an indication for a dark state, for a short-lived dark state. And next piece of the puzzle, if you do this experiment under ambient air, this is under nitrogen. Then you put on air and you get the fluorescence back. And then you leave it on air, you start bleaching slower than here. And then you put on nitrogen, so no air to the sample. Fluorescence goes away rapidly. So you conclude from this that this short-lived dark state, it's reversibly short-lived and it's oxygen sensitive. And this suspects, well, who says oxygen sensitive suspects a triplet. Triplet is known to be quenched by oxygen. So triplet is known to be a short-lived dark state and it's known to be oxygen sensitive, so we suspect it to be a triplet. But who says triplet says FCS. FCS is a spectroscopic technique, fluorescence correlation spectroscopy. And it's basically the same setup. You put the sample under the microscope, only this time it's a confocal microscope. The sample spot is diffraction limited, 200 nanometers in diameter, and you measure the time trace of the fluorescence with a very high time resolution. It's nanosecond time resolution. And then you take this time trace and compare it to a time-shifted copy of itself. And in this correlation function, you will see the fingerprint of short-lived dark states. When the technique was developed, people needed bright chromophores. They worked on fluorescence, and with fluorescence, they got these dark states. They got the triplet state of fluorescence, who lives a few microseconds. So when people put the GFP under their FCS machine, and they saw this signal, this is a microsecond lived signal. This is 10 to the minus 3 milliseconds. So this is a microsecond here. There's a power-dependent decay time here. We'll say, oh yes, that's what we saw in fluorescence, that's the triplet, and it's microsecond lived. And so it came about that people believed that the EGFP triplet lives microseconds. Nobody cared to check whether it's oxygen dependent, and it's to be fair, it's not obvious. If you have a spot of 200 nanometers in diameter, you cannot put an oxygen electrode in there. So if we want to check whether this microsecond phase is oxygen dependent, we need to have resort to a different technique. And that technique is should be something which has a macroscopic sample. So we do transient absorption or flash photolysis. we put a milliliter, a macroscopic amount of protein into an optical cell, put the optical cell into the spectrometer, observe the absorption with high time resolution, and we give a flash, therefore flash photolysis. And the flash will trigger some events. And if those events create a species, then if they create a species that absorbs, then the absorption should go up. If the flash creates depletes a species that absorbs, then the absorption should go down, which is the case here. The transmission goes up and the absorption goes down because the flash bleached something in the sample. But this is just the principle. We did this, we put the GFP into the sample cell, gave a laser flash, and observed what happened. And we actually saw some signal in the microseconds. Here it is. This is the microsecond signal. You see, the lifetime is something like 2 microseconds or so. But this actually 4 curves overlaid here. 3 of them are under argon and 1 is under oxygen. If you can see the difference, you're better than me. I cannot. So my conclusion here is, sorry, but the microsecond phase is not oxygen dependent in its lifetime. Means it's not a triplet. The inverse is not true. If something is a triplet, it's oxygen dependent. That is for sure. But if something's oxygen dependent, it's not necessarily a triplet. But this one is not a triplet because it doesn't care about the oxygen. So what do? You see, there is still something going on here, longer lived. So we extend the time range and we look on the millisecond window. And on the millisecond window, we see a signal that goes up and down, and it goes down in a few milliseconds. And here the original sample is the black curve. Then we replace the air in the sample by argon. This is the red curve. Then we replace the air in the sample by pure oxygen. This is the blue curve. Or you see the decay time scales with the oxygen concentration in the sample. So this looks more like a triplet. Could be something else. Could be a radical also. Radicals are also oxygen dependent. But radicals, as a rule, are so reactive, they do not live milliseconds. They react further and they are gone by microseconds. Or so we needed proof that this is a triplet. It's complicated because any triplet quencher is also a radical quencher. This is chemistry, because a triplet by nature it's like a biradical. It has two incomplete shells. Okay. So the ultimate test whether something is a triplet or not is whether it emits phosphorescence. Phosphorescence is like fluorescence, only much weaker. And this is because the return to the ground state from the triplet is spin forbidden. Therefore, it lives a lot longer than the fluorescence, and it's much weaker. And that is a really technological challenge to see a weak signal after you have had a very strong signal. The fluorescence is strong. The phosphorescence is weak. And it took quite some ingenuity to do it, but my colleague Klaus Brettel managed to do the ultimate proof that in GFP we have a not micro, but millisecond lived triplet state. We could also determine the yield of the formation, and it's about 1 in 1,000. So 1 of 1,000 molecules that go down the fluorescence pathway forms the triplet. That doesn't seem much, but if you excite your sample, your eGFP sample, with 1 kilowatt per square centimeter, it's not amazing amount of energy, then you excite a molecule every microsecond, meaning that every millisecond, one of the molecules goes into the triplet. And that means if the triplet lives 4 milliseconds and is populated with 1 millisecond, after a few milliseconds, you have 80% of the molecules in the triplet state. And that's what you observe here. This is time in milliseconds, and this is the fluorescence. I measure fluorescence. And fluorescence is a measure of the singlet state population, because only the singlet state population emits. So I switch on the laser, I have a strong signal, and after a few milliseconds, most of my singlet population is gone. Here, this is energy dependent. So you see, the stronger you excite, the more you lose. And this is temperature dependent, because this is done at 100 Kelvin for the simple reason that I want my molecules to stay put. If I warm up the sample, they start to move and to diffuse out of the beam, so I cannot follow them anymore. You see this here. If the temperature goes up, you lose the triplet population just because by diffusion and exchange, all the molecules go away. So from now on, I will talk about immobile systems that might be either by low temperature, might be at room temperature. If you immobilize the protein in a matrix like a gel or something, then you observe the same thing. So, but under conditions of immobilized protein, you get a decent population. You lose a lot of a singlet. You get a decent population of the triplet, and it lives milliseconds. So you can measure a spectrum of that species. That's what we did. Here it is. And I think in the next one, it's compared to the singlet absorption. Yeah. So the absorption spectrum of the triplet, it covers the whole visible range from 300 to 700, and it has a nice vibrational progression in the infrared. But the important thing for now is the extinction coefficient itself. It is comparable. This is the singlet emission absorption coefficient. This the triplet absorption coefficient. So whenever you excite the GFP with your 488 laser into the maximum, you also excite the triplets. And if you go with your laser somewhere here, then you have only the triplets, or mostly. What does this imply? It implies a lot of things, but the two important things to see here is as long as you pump with the laser the singlet state by forward intersystem crossing into the triplet state, as the triplet absorbs as well, you also do pump it back into the singlet. So you have two light-induced processes, the forward pumping and the backward pumping. Then you have the dark process, the spontaneous intersystem crossing. This is the natural lifetime of the triplet state. And you have another process. This is the triplet absorbing and not returning, but undergoing photochemistry. So this is different from the Hirschfeld picture. In the Hirschfeld picture, all photochemistry started here. Now we start photochemistry here. And this has a different absorption spectrum, a different power dependence, and everything is different now. So let's see first how the populations of the four involved states depend on excitation energy. In the ground state, if you excite little, most things are in the singlet state. The more you excite, the more you pump into the triplet. So you lose the singlet population, you gain the triplet population. And it's never reaching 100% because you have the back pumping process. So there will be some saturation. Even at very high energy, you will never get to 100% triplet. In the excited state, for the singlet, this is the fluorescing state. You get more and more and more because you excite from the ground to the excited state. For the triplet, you get more, but that is limited because the population is limited. And by viewing these four curves, this, and this, you see that only one of them is linear. Most of them are not. So if you now want to study the bleaching, the power dependence of the bleaching, you have to consider all four of them. It's not obvious. You will not expect a linear dependence on excitation power. So in order to study not just the bleaching, but we always have to consider bleaching in the context of fluorescence. So what we do is we define a parameter which we call goodness. Goodness has the good thing, the fluorescence on top, and the bad thing, the bleaching on bottom, and the ratio of the two will give us a measure for the quality of the fluorophore. It gives much fluorescence, little bleaching. It's a good thing. Little fluorescence, many bleaching, it will be a bad thing. It will be a low goodness. In the Hirschfeld case, when what do? I multiply the population of the precursor state by the probability of the process. So precursor state of fluorescence is S1. Probability of fluorescence is fluorescence quantum yield. In the Hirschfeld picture, precursor state of photobleaching is also S1, and the probability of photobleaching is the quantum yield of photobleaching. So these will cancel, and we get what Hirschfeld found, that the photon budget depends only on the ratio of fluorescence and bleaching quantum yields. So this is the Hirschfeld photon budget, but we can modify now the precursor state. If, for instance, we consider that the photo bleaching precursor is not the singlet, but the triplet, then power dependence will not be flat, but depending on whether we consider this one as the precursor state, that will give us the red curve. We will get an amazing linear dependence of the photon budget on the excitation energy. Or if you consider this excited triplet as the precursor state of the photobleaching, you get the green curve, meaning that the stronger you excite, the more you lose photon budget. So depending on whether this one or this one is the precursor state, you could gain or lose photon budget. So your photon budget is now power dependent. And that's actually what is observed. People did careful measurements for loads of GFPs. They measured the bleaching, and they found almost none of them has a linear power dependence. Some have stronger than linear, others have less than linear, but none have, well, very few have linear. And that might be explained by the fact that you can have bleaching from here and from here and from here. And so your power dependence will be a sum of the three curves. Not linear at all. But now we're still worried by the fact that the stronger you excite, because if you want a lot of fluorescence, what you do is you excite stronger, and what you do is you destroy your photon budget. So we have to think, how can we deal with that? Can we do something about it? And yes, we can. We do not need to wait until we have lost all the singlets. We can switch off the laser, for instance, here. If we do that, we will have the fluorescence from the singlet. Then we switch off the laser. And during the dark period, the singlet will repopulate. Well, you don't have fluorescence here because no laser. So we lose this part. But compared to the steady state case, where you will always get only fluorescence from the base level, you have all this which you have gained, which is above the base level. So it's a trade-off. And the parameter in the trade-off is when you switch off and when you switch on again. Because the longer the dark period, the more the loss. And the shorter the light period, the shorter the fluorescence. So you have to find a balance, and this balance will be power dependent because the speed of this decay is power dependent. So if you optimize the light period and the dark period, you can actually arrive at something amazing. That means that for pulse conditions, the photon budget goes up. You remember in the pulse case for the higher triplets being the precursors, you lost photon budget with higher energy. If you pulse with an intelligent scheme, you can gain overall average fluorescence. No, you don't gain fluorescence, you lose fluorescence, but you gain in photon budget because you lose less fluorescence than you lose bleaching. Because the triplet is less populated, you have less bleaching, and the overall photon budget is increasing with excitation energy. You remember that was the take-home message? That for GFPs, for intelligent choice of the illumination scheme, you can have an increase in the photon budget with increasing excitation power density. And that is something to be considered, investigated, and found out. Because up to now, this curve is a theoretical curve. There is no experimental work on that so far. This is basically the last slide, except one, the people. There were many people involved in the project. Some produced purified proteins, some manipulated the microscope, some brought in money. This is Klaus Brettel, who measured the phosphorescence of the GFP. The really amazing feat, but he is by now retired. So it's up to us, to you, to take over. Thank you for your attention. I'm ready to take questions. I'm not saying you're doing microscopy wrong. I'm saying that if your sample is immobilized and it stays in the spot, your excitation laser is stronger than a kilowatt per square centimeter, what you see is basically 20% of what you could see. 80% are somewhere, but you can't see them. And that might be mitigated by pulsing the light, by adding oxygen, which is an efficient triplet quencher, or by thinking about engineering a GFP which with a shorter lived triplet, which is really a challenge. Because why is the triplet so long lived in GFP? Because the chromophore is shielded from the solvent, so all the quenchers they get there, but they take time to get there. So you would have to have a barrel with holes in it, and as soon as you have the barrel with holes, the chromophore might isomerize, and you lost fluorescence as well. So it's a really challenge, but I think it's worthwhile because you can gain a factor of 5 in the intensity, and not only intensity, also in the photon budget. So you will not be bleached after milliseconds, but you have time to observe your sample. So no, you're not doing wrong. You're doing right, but you could do better. Hopefully, someday.
Thank you. The question is, what do we need, for example, to build some online calculator for the microscopy? So to choose some optimal regime, like pulse frequency, average pulse power, whatever.
Well, the manuscript which presents the results, it has a table which contains all the formula. So somebody who would take the time to make an Excel table and feed in the absorption spectrum of the singlet ground state and the triplet ground state. That are the input parameters. You need to know where your triplet absorbs and how much, and then the formula in the paper. That is straightforward.
So basically, for example, if there were the data for any GFP like in use at FP base, let's say, I mean both singlet and triplet absorption, it would be enough.
Considerable help, yes.
Thank you.
But you see that the measurement of the triplet absorption spectrum was tricky because it needed to be long-lived in order to have enough photons to see to make the spectrum come out of the noise. So at 100K, the triplet lives 20 milliseconds. And what I did is I switched on the laser very strongly for 10 milliseconds. then switched it off for 20 milliseconds, and during that 20 milliseconds, I registered the absorption, which is still a mixture of ground state and triplet state. And I did that for an hour.
Collecting and collecting.
Collecting and then averaging and smoothing, and that gave the curve. So it's not straightforward, but it's doable. So might be, well, you need to sacrifice a student.
Thanks. I saw you have two absorption curves, one for the triplet and one for the singlet state. Could you use like a second laser to sneakily already put your...
This is a brilliant idea. People do it. They actually use an infrared laser in that amazing 800 nanometer peak, and that is actually a way to pump it back all the time. So it's better than pulsing because you don't lose the singlet, but you pump back without touching the singlet. So that is published. I can give you the reference. Thank you.
Martin, I need you on stage. So, this is a certificate of us for your attendance and being here, and for the great lecture. Our students and this organization has made a donation on your name to our foundation to support our undergrad students. So that's also a thank you card from our foundation. So welcome all. Now it's my great pleasure to invite Kıvılcım Yüksel on stage. But before doing that, I'd like to introduce Kıvılcım Hoca to all of you. Kıvılcım Yüksel completed the MSc degree in 2000 in Ege University Electronics Engineering Department, where she worked as a research assistant as well. Afterwards, she worked at Northern Networks NETAŞ Istanbul as an optical research engineer. Between 2002 and 2005, she was with Multitel ASPI Mons Belgium, Applied Photonics Group, mainly involved in the project on monitoring methods based on optical time domain reflectometry technique for point-to-multipoint optical access networks. Since 2012, she's been working at the Electrical and Electronics Engineering Department of IZTECH. She established the Fiber Optic Metrology and Sensor Applications Laboratory. Specific research areas that she focuses on with her team include design and implementation of optical fiber reflectometry techniques, distributed optical fiber sensors, fiber Bragg grating sensors, and sensor data analyzers. So, Kıvılcım Hocam, please.
Thank you very much, Canan Hocam. It's my pleasure to be here to take part of this event. Thank you for the organization and for the invitation. Our research activities realized in Fiber Optic Metrology and Sensor Applications Laboratory, FISENS-Lab. But before that, I would like to give you some background information about fiber optic sensing technology. To do so, I would like to start by asking some questions. My first question is related to this structure, which is located in the northeast of France. What you see here in these photographs is a scientific laboratory which is 500 deep underground. These photographs are from this place, indeed. There are only two shaft access to this place. And this laboratory, including hundreds of meters of galleries, is planned to be used as storage of radioactive waste that will be used by the ANDRA, French National Radioactive Waste Management Agency. And in such a scientific laboratory to test underground storage of radioactive waste, we need to measure some parameters. What are they? These parameters are, of course, structural strain. The structure should be solid enough, yes, and some environmental loading, rock, soil deformation should be measured. Temperature and also chemical and radiation sensing is very important for such a laboratory. And for the sensors to be used there, the specifications of the sensors are very important. They should be non-invasive. Their durability should be more than at least 100 years. Yes. And these sensors should be operated properly in very hostile conditions, high temperature, gamma radiation, and so on. And moreover, on top of all these specifications, once the radioactive waste is stored there, there will be no access to this location. So we need remote sensing. All these parameters should be remotely interrogated from and far from this place. Well, so my question is how to monitor such an underground nuclear waste repository. Let's continue with another question. You see in this picture a wind turbine with very high capacity. Nowadays, there are more bigger than that one, offshore wind turbines. This one has 2.5 megawatts, and it has blades of more than 50 meters. Okay, such a structure should be accurately monitored to obtain accurate record of the load cycling. And this information can be used to establish the correct time to realize maintenance on such a structure. This is called preventive maintenance. Okay, and this saves a lot of cost, a lot of money for the operators of such wind turbine operators. And of course, there are many of them. So all of these groups should be monitored once again from a remote location. And the sensors that should be used in such an application, they should be embedded into the structure. Most of the time, these blades are made of composite materials. Okay, and these sensors embedded in the structure shouldn't add heavy load on the structure. So they should be light enough, and they should be lightning safe and should be interrogated from remote locations. So my second question, how to monitor bending load of blades in a wind turbine? Let me show you two more examples, two more applications. In one of them, we need to monitor overheating over the power lines, okay? Because overheating in cables and joints, especially at joints, leads to reduced lifetime, supply failure, and disruption. When monitoring such power lines, we are talking about 100 kilovolt, yes, and the sensors should be immune to electromagnetic interference. The last example concerns the fire detection in tunnels and buildings. In this application, the sensor shouldn't be influenced by dust or smoke. Okay, so I would like to come to the point to say you that fiber optic sensors are very good candidates to deal with several applications like I have already shown you. Okay, but still there is not a single solution that fits all the applications. Okay, for each of the applications there exists a suitable fiber optic sensing methodology. Why they are good candidates? Because they have got many advantages by using the fiber optic technology itself. This is a mature technology already there for television. This case, into two groups, let me say. In the first group, the optical fiber itself is the sensing medium, pinpointing the measurement, localizing the measurement in real time. The optical fiber is giving the parameter to be measured as a function of distance. This is a continuous signal interrogated by the interrogating unit. In the second option, which is quasi-distributed optical fiber sensor, we implement the sensing points are implemented inside the core of the optical fiber. So we have the information of the parameter to be measured at particular position only. Okay. For this second structure, architecture, the optical fiber by ultraviolet light source, UV light source. The important parameters of FPG are the length of the FPG, so over which this modulation is induced, the periodicity of this modulation, so the grating pitch, okay, this is typically around 500 nanometers, and the amount of refractive index modulation, which is a very small number, 10 to minus 5 to 10 to minus 3. Okay, we have got an FPG inscribed or written inside the optical fiber. So how can I use it as a sensor then? Once it's inscribed into the optical fiber, the FPG acts as a passband filter in reflection. What does it mean? If we inject a broadband source into the FPG, into the fiber, then a small portion of light around so-called Bragg wavelength is reflected while the rest of the spectrum continues to its way. Rest of the spectrum is transmitted. So this Bragg wavelength is a function of effective refractive index and the periodicity of the FPG. So if external physical parameters somehow affect these two parameters, then the Bragg wavelength will be influenced. This is the basic mechanism. Let's check which physical parameters can change the Bragg wavelength. These are temperature, axial strain, and pressure. Let's take the temperature first. You see the refractive index change due to the temperature change through thermo-optic effect is one parameter. And due to the thermal expansion, the periodicity of the grating also is influenced. This is the second parameter of the Bragg wavelength shift is a function of temperature. Similar arguments are valid for axial strain and pressure. Okay, so this means that if we heat the FPG, so if we increase the temperature, the Bragg wavelength shifts. Okay, here you see the increasing, the response of the Bragg wavelength shift is a function of increasing temperature and also decreasing temperature. You see that the Bragg wavelength shift is linear, which is very good to calibrate the sensor. And there is no hysteresis in heating and cooling cycles. So this is really very practical sensor type for quasi-distributed sensors. Of course, I showed you the very basic one, the uniform FPGs, but there are many other types of the gratings, such as chirped FPGs, where this modulation is not periodic, but the periodicity is increasing or decreasing along the length. Tilted FPGs, long gratings, and so on. And they have got the applications from medical domain up to structural health monitoring. Very wide range of applications are possible by using the FPGs. The message for you today about FPGs would be the following. The main advantage of the FPG sensors is that the information is encoded in the wavelength, not in the intensity. So therefore, if there are power fluctuations in the system at the laser site, at the photodetector, or in the outside plant, the result is not influenced by the power fluctuations because the information is in the wavelength itself. This is one thing. Second thing, although I show you only one FPG, we can inscribe many of them in the same fiber, right? Thousands, tens to thousands of FPGs can be inscribed, fabricated into the optical fiber and can be interrogated by the same unit, which means that the cost of this interrogation unit is divided into many sensor points. These are two main advantages of fiber Bragg grating sensors. And they are very popular. I will show you some applications in the following slides, not now. Now, let me pass to the second group, which is distributed optical sensor. Here, imagine that the optical fiber is my sensor. It is placed at the outside plant. For example, in the nuclear waste repository, there is an optical fiber in the shaft and so on. This would be 1 kilometer length, 10 kilometer, 100 kilometers, whatever, and you put it whenever you want. Then, in the interrogating unit, there is a light source and there is a detector. When the light is injected into the optical fiber, a small bit of the signal is reflected back all along the fiber. Okay? And this signal in turn, once arrive to the photodetector, this will create our sensing signal. So what actually is back reflected? These are elastic and inelastic scattering mechanisms known as Rayleigh scattering for the elastic one, and Brillouin and Raman scattering for the inelastic ones. These are the contributions. Raman scattering in general is very well established for distributed temperature sensors. As far as I know, tomorrow afternoon, some technology will talk about distributed temperature sensors. Today, I will concentrate on Rayleigh scattering, but just it is important to say that all those scattering mechanisms can be utilized in distributed optical fiber sensor schemes. Okay, so we understood that interrogating unit includes light source and detector in it. Rayleigh scattering effect indeed refers to the scattering involving particles much smaller than the wavelength. As we readily implement the fiber optic technology for the sensors, in general, we use the same wavelength windows utilized for the telecommunication, such as 1.5 micrometer, 1.6 micrometer, and so on. Therefore, for the atoms and molecules that are concerned, meet this criteria, right? The dimensions concerned are really small enough compared to the wavelength used for the fiber optic sensors. And the Rayleigh scattering, this phenomenon brought the Nobel Prize to the physician Rayleigh, okay, in 1980s. He showed that the Rayleigh scattering is inversely proportional to the fourth power of the wavelength. So what is it? The two main contributions of Rayleigh scattering in optical fiber are the local density fluctuations. This is due to the fabrication process of the optical fiber. When it is frozen, then the structure is not perfectly homogeneous. There are some frozen density fluctuations during cooling. Second contribution is the fluctuations of the doping. As you know, fiber core is doped to slightly increase the refractive index of the core compared to the cladding. Then due to these two effects, what is the result? When the incident light interacts with the density fluctuations all along the fiber, the light is scattered in all directions, and a very small portion of it is guided back. This is called Rayleigh backscattered signal that is used for distributed sensing applications. Okay. Once again, Rayleigh-based distributed sensing also can be classified into two groups depending on their operational mode. In the first family, the analysis is performed in the frequency domain. This is called optical frequency domain reflectometry family. And the second one is the optical time domain reflectometry. Let's take the OFDR first. You see an OFDR setup here. Just concentrate on this part. This is a Michelson interferometer. Most of you are familiar from your physics courses, here a tunable, the frequency of linearly modulated. Okay, this is our Prof signal. This linearly modulated signal is injected into the interferometer, is divided into two. One part is reflected from a mirror, which is also called local oscillator, and the Prof signal propagates through the device under test. Then the signal coming from the local oscillator and the device under test, they interfere, giving rise to so-called beat frequencies. Each beat frequency indeed corresponds to a local reflection point. In the same manner, Rayleigh backscattering signal can be characterized by a distributed beat frequency distribution all along the fiber. Okay, so the optical frequency is modulated, and the signal, the interference signal, is measured by a photodetector. Which is shown here by a detector. And this is then converted into sampled by using a data acquisition card. Then, using signal processing units, these samples are converted into frequency domain. This is the main important point in the frequency domain. So in the frequency domain, indeed, what we are observing or measuring is the beat frequencies, okay? As the beat frequency is related linearly proportional to the delay time, so round trip time of this probe signal, then the frequency axis can be converted to the distance. So imagine that we measure a peak here at a certain beat frequency. This beat frequency can reveal us the position of this reflection. Okay. But the life is not so easy, of course. The perfectly linear modulation of the TLS is not possible. In real tunable laser sources, there are always nonlinearities when modulating them. This nonlinearity would be parabolic, or there would be some fluctuations around this modulation. And this nonlinearity in the frequency modulation gives rise to broadening of those peaks, which reduces the spatial resolution of the system. Okay, so for OFDR thing, the spatial resolution depends on the linearity of the optical frequency modulation. And the range of the measurement depends on the coherence length of the tunable laser source. Okay. So what is all about then? All these auxiliary interferometer, there is another interferometer you see here. This interferometer is used to compensate this nonlinearity effect and enhance the spatial resolution. Okay, because data acquisition card takes the samples at equally spaced time intervals, but at equally spaced time intervals, the optical frequency are not equally spaced due to this red line, due to this nonlinearity. Then the signal is resampled by the way of an auxiliary interferometer to make to compensate the effect of this nonlinearity. Typically, OFDR techniques provides us hundreds of meters of range with millimetric spatial resolution. Okay, so application areas are should be chosen according to those specifications. When it comes to OTDR, optical time domain measurement technique, this is indeed very used in optical communication network diagnosis. I mean, to locate the faults along the optical link, to measure the attenuation of the link, insertion losses, return losses, connectors, splices, and so on. If there is a dirty connector somewhere, you can localize it by using OTDR. So this is off-the-shelf device, cheaper than the OFDR, and you can find many devices, even handheld devices in the marketplace, operating at telecommunication windows, of course. How does it work? Let's briefly explain. The output of the laser source is modulated to obtain an optical pulse. This optical pulse is injected into the fiber under test. As this pulse propagates through the fiber, the so-called Rayleigh backscattered signal that I mentioned to you arrives to the receiver, and this signal is converted, is sampled and analyzed. Okay, as we know the speed of group velocity of light in the fiber under test, we can convert the time axis to the distance. So here the receiver measures the signal, backscattering signal, as a function of time, but we can convert the time into distance by using a simple formula. Okay, there's a factor of 2 due to the round trip time. Okay, injection of pulse and back reflecting signal. Here you see a schematic view. Optical pulse is injected into the fiber. If there is no problem, there is only one section of fiber. If you take the logarithm of the backscattered light, you see attenuation characteristics of the fiber in a line. The slope of this line gives us the attenuation coefficient of the fiber. But imagine if there is a localized event, such as a loss at a particular position, then we can measure it, both localize and measure it on the OTDR trace. This is a schematical OTDR trace. The reflection, what you see here, is due to the glass-air interface at the end of the fiber. This is Fresnel reflection. And after this, there is no fiber anymore. We measure normally the noise signal coming from the photodetector. Okay. Here it is different from the OFDR. The spatial resolution depends on the pulse width. Okay, in order to have better spatial resolution, we use narrower pulses. But in this case, there is less energy in the pulse, so the measurement range decreases. So there's a sort of trade-off between the spatial resolution and the measurement range. Typically, OTDR brings us a kind of trade-off, which was not the case for the OFDR. Okay.
Dispersion also is another factor, right?
This can be neglected in this case.
Compared with other effects.
Yes, dispersion can be neglected. In the beginning of the 1990s, indeed, in the literature, there was huge amount of papers, research, trying to use a conventional OTDR for a sensor application. Most of them disappeared, but I still wanted to show one example, one of them. Most of them were very exotic solutions. In this example that I chose, you see optical fiber. Okay. The optical fiber is on a supporting former. This is on this supporting material, hydrogel is deposited onto this. Hydrogel is a special material. When there is humidity or water in the environment, it swells the humidity, okay, and the volume increases. All this structure is surrounded by Kevlar thread. This is Kevlar thread is wound to keep everything together. This was proposed to measure if there is a water ingress in the telecommunication pipeline. We don't like water at all for fiber optic networks. So when there is water inside the pipeline, then this special hydrogel swells it, the volume changes, the optical fiber is distorted. This induces microbands, and there is a banding loss due to all these effects. So remember, in the OTDR trace, we are able to localize any kind of loss. So when there is a banding loss at a particular position, we can localize this problematic location where there is a water ingress in the pipeline. Okay. This was a kind of sensor application proposed in the early 90s. And there are many of them. But nowadays, more popular OTDR type is the phase OTDR. It has been becoming more and more popular in the marketplace. This is a little bit more complicated one than the conventional OTDR. In this case, the optical pulse from a very coherent source, having very narrow line width, very narrow line width is injected into the fiber, and the power measured power varies randomly with distance due to coherence noise, because now the signal is coherent signal. Okay. And due to this coherence noise, the OTDR trace is something like this, noisy like trace, but it gives us a lot of information. The phase change, so you understand that there is a phase information now. In the previous one, in the conventional OTDR, we are not interested in the phase. Even in the conventional OTDR, there is an averaging process. We send a lot of pulses and we take the average of all the results. But here, there is a phase information. So phase change is a function of both the dimensional and refractive index changes. What do I mean? Imagine that all the local density fluctuations of the fiber are represented by these white circles there. Okay, and imagine that there is someone digging near the fiber. This creates some kind of vibration waves or acoustic waves. When the acoustic waves hit the fiber, these molecular structure is shifted. Of course, this is in very microscopic scale. And due to this shift, the effect of this shift can be measured by using phase OTDR. Phase OTDR is used for distributed acoustic sensing or DAS applications. So there are two main groups of phase OTDRs, very briefly, depending on the detection type, direct detection and coherent detection. In direct detection, the power of the reflected Rayleigh backscattered signal is measured, whereas in the coherent detection, a coherent detection methodology is used to obtain phase information as well. So even though I showed you only one OTDR, phase OTDR trace here, indeed what we do is to take a lot of them. This one phase OTDR is called pulse axis, okay? And we take, imagine that I take many OTDR traces like this one over 1 minute or 30 seconds. And by comparing all these new OTDR traces with the very first one, we are able to localize our guy which is digging at a particular position. Okay, so differences shows us the position of this activity, of this vibration. Then if we concentrate on that particular location, okay, where the vibration waves hit the optical fiber, if we only analyze that particular position over all the OTDR traces, which is called slow time analysis, we are able to measure the frequency of the vibration. Okay? And the transfer function between the Rayleigh scattering and the vibration is not linear if we measure the power. But if we are able to extract the phase information, then we can also quantify the magnitude of the vibration, because there's a linear relationship between the magnitude of the information and the phase extracted from the traces. Okay. So, of course, this is a challenging process. As you can see, there is no averaging process, and Rayleigh backscattering light is very weak signal, and polarization and interference, fading, noise affects our measurements. Therefore, nowadays in the literature, Rayleigh enhanced fibers are proposed. So, in conclusion, I can say that if there is a DAS, distributed acoustic sensor, implemented underground, for example, in movement of a vehicle, digging activity, people walking near the sensor, climbing activities, all of them can be measured by phase OTDR interrogator. You can imagine this as hundreds of microphones laid along the optical fiber. Even we can detect the leakage from the protected pipeline, water leakage, for example. Okay. So this gives us the opportunity to realize some security applications, real-time security applications. But of course, for security applications, the challenging point, what is it? The classification of those events. For this one, machine learning algorithms are used. Another challenge is the data, amount of data. If you are monitoring an asset, so you have got huge amount of data to deal with. As the Rayleigh scattering is a very weak signal, then in the literature, fiber Bragg gratings are proposed to be used to enhance this signal-to-noise ratio. So this is very generic phase OTDR, very coherent laser source, pulse modulation, signal is amplified because the signal, Rayleigh backscattering signal is very weak. Remember, this is an optical amplifier. There is an optical filter to filter out the noise of the amplifier. And then the signal is demodulated. This demodulation method can vary from system to system. There is self-heterodyne, heterodyne coherent detection, Michelson interferometers, 3x3 couplers, and so on and so forth. Then after photodetection, there is a digitizer and huge amount of signal processing running here to identify the events correctly. Now I came to the research activities in my lab based on this background information. How many minutes do I have? 19. Okay, okay. So what you see is a master thesis. In the framework of a master thesis of one of my students, we developed a simulation tool for phase OTDR vibration sensors. And in this simulation tools, we considered both the Rayleigh backscattering and the signal coming from the FPGs. So this functionality is switchable. We can switch off and on the contribution of the FPGs. And the originality of this work was we considered two noise sources, multi-reflection crosstalk and spectral shadowing crosstalk. Multi-reflection crosstalk basically due to the signal making, for example, 3 reflections among the FPGs and arrives at the same time impingence on the useful signal coming from the particular sensing point. And spectral shadowing is due to the transmission spectrum of all these upstream FPGs before arriving to a particular position. Imagine that perturbation is applied here, but for the pulse, probe pulse, before arriving to this particular position, it passes through a lot of FPGs. So its spectrum is subject to transmission coefficients of all these upstream FPGs, and this affects the result in a bad way. We simulated all those effects. This is one thing that we realized in a couple of years ago. Another project that I am involved is the Water for All Sustainable Water Management Project, which was supported by CoFund. This is a doctoral training program. 20 PhD students will be supported there, and I will be co-advising 2 of them with collaboration. I have got 3 international collaborators, 1 national collaborator. Someone from some technology will come tomorrow. Also, I will be co-advising 2 students with international water resources, water resources management department from IZTECH. In this program, we are going to study the problems related to the water management, but using fiber optic sensor technologies. Okay, for example, implementation of DAS for pipeline monitoring applications, seismic feasibility study to identify geothermal reservoirs, artificial intelligence algorithms to optimize some transdisciplinary water management system, and so on. So all the PhD theses will be designed around a roof of sustainable water management purposes. As I mentioned, some has got some commercial devices for DAS applications. This is FOTAS product family. I put just 2 examples. For example, they are studying a project where under the Marmara Sea near Istanbul, along which a fiber line is established, which is used for earthquake detection. And these signals are evaluated by Kandilli Earthquake Research Institute. Another one is monitoring of 40-kilometer section of the North Marmara Highway by FOTAS system. This is a basically phase OTDR interrogator that we have just explained the operational principle. So as far as I know, Soner Mülayim Bey will talk about their DAS and Raman temperature sensor product families tomorrow afternoon. Let me pass to another project that we concluded this year, last month. This was an IRA-SME project, international research activities by small and medium-sized enterprises. We had a collaborator from Belgium, BSense, and from Technology Development Zone of IZTECH. My laboratory's role was to bridge the gap between them. The idea is to instrumentation of industrial microwave ovens by fiber optic temperature sensors and fiber optic fire sensors that are controlled by a control unit, and this feedback information allowed us to design better magnetron configuration to increase higher safety and higher energy efficiency, for higher energy efficiency. In the product line of MET technology, there are some applications, AI assisted robots, and so on. We, of course, in this project, focused on this industrial microwave oven product. As you can see, this industrial microwave oven is composed of many modules. the product to be dried, for example, food, fig, resin, and so on. The product is loaded from here and passing through all these modules and through the conveyor belt. Related to this configuration, there are two main challenges in it. One challenge is the inside in those modules, the heating is not homogeneous. There are some hot spots or cold spots which affects the quality of the final product. For example, food. Okay, aflatoxin can appear due to cold spots, for example. Another problem is the fire security requirements. It is not very common, but it is possible that some fire begins at the overheated points of the conveyor belt. These photographs are from the real cases, real instances. In order to solve these two problems, we implemented fiber optic sensors inside the microwave oven. Here you see the measurement setup with instrumented microwave oven. This is microwave oven. You see the optical fibers going through the FPG interrogator, fiber Bragg grating interrogator. Okay, so we implement this interrogator has got 16 channels. At each channel there is a fiber connected, and in each fiber there are 16 FPGs. You remember in the beginning I mentioned that we can interrogate many of them. So in total we have got 2056 measurement points inside the oven, which is really very efficient compared to the previous techniques where they used only point sensors inside the oven, only one measurement point. Okay, and you should note that the electrical sensors cannot operate inside the oven due to high microwave radiation. Right. Here you see the fire detector casing with a window there. In this window, there are also two FPGs. This is a kind of fiber bolometer. One of the FPGs is coated by a special infrared sensitive material which absorbs infrared radiation. The other one is temperature reference. And when there is a fire or a starting fire inside the oven, of course, this casing is implemented in the top corner of the microwave oven inside it. When there is a fire, the infrared radiation is captivated by this detector. So this was a successfully closed project. Another project that we realized in Belgium this time is related to the railway monitoring by FPG accelerometers. What is an FPG accelerometer? It is this tiny box, very small box, that we implemented on the slipper. You see, on the slipper rather than the rail. This is the main advantage. It is really easy to implement such an accelerator. Inside this box, there is a flexible cantilever beam, where at one end there is an FPG mounted on it. At the other end, there is a mass, seismic mass. Okay, all those stuff is connected to an optical fiber, which is interrogated by a closure, by a box near the railway. Okay, so we took those measurements during normal train operation at a railway line between Mons and Liège in Belgium. Okay, you see this is highly noisy stuff, noisy trace due to the high sensitivity of this accelerometer. How does it work? Imagine when the train passes through, when vertical acceleration is applied on this accelerometer, this induces strain. This creates strain, And due to this strain, the cantilever beam changes its position, and the induced strain can be measured by measuring the Bragg wavelength of the FPG. The induced strain is proportional to the distance of this cantilever from the neutral position. This is the tricky point. So by measuring the FPG Bragg wavelength oscillating between maximum and minimum values, we can already see that we can already determine that train axles are passing through. But we developed some further signal processing algorithms to demodulate this signal into that one, to locate the axle positions. And then we calculate the speed of the train for different kinds of trains, okay, under their normal operation. This is the last application that I will show you today, which was realized by master student Şamil Şirin. This is an electrical current sensor interrogated by phase TDR, where the interrogation unit is the phase TDR. The electrical current is flowing through this wire, which is perpendicular to this plane, okay? And around this wire, there is a special kind of optical fiber coiled around it. You see, this is a kind of spoon fiber. And there are two FPGs at the two extremities of this spoon fiber. The sensing mechanism, there are many details around it. I need another 40 minutes to explain the theory, but the main sensing mechanism is based on the Faraday effect. Okay, if a magneto-optic material, which is the fiber optic in our case, magneto-optic material is under magnetic field, it is under magnetic field due to the current passing through this wire, okay, remember Ampere law, okay. It gives rise to non-reciprocal circular birefringence proportional to the magnitude of the magnetic field. So this magnetic field created by the electrical current creates here phase shift between circularly polarized modes inside the fiber. It also creates a rotation of linear polarization axis. Indeed, this phase shift is then measured by using phase TDR. Of course, here we target at very high level of electrical currents. These are not milliamperes. These are kiloamperes and megaamperes. These currents are flowing through such projects, ITER projects, International Thermonuclear Experimental Reactor. Okay, in these reactors, plasma currents attains the values of megaamperes, where the classical sensors cannot be used and fiber optic sensors are good candidates once again. Okay. This was the last application. Okay, the results were published in here. This technique was an original configuration proposed by our master student in collaboration with University of Mons. Last but not least, in my laboratory, student exchange possibilities, there exist student exchange possibilities, Erasmus exchange possibilities with Limoges University in France and Mons University in Belgium. Tens of students realized their undergraduate internships and one semester education on photonics technology at University of Mons laboratories. If you are interested, I see that there are lots of undergraduate students here. If you are interested in fiber optic sensing technologies, please feel free to contact me and to take part of our ongoing projects. Here are my collaborators that I mentioned along the presentation. Take a look at our web page. This is a modest web page, but we try to keep it updated. If you are interested, please take a look at our webpage. Okay, thank you very much for your attention.
Present her certificates to Professor Kıvılcım Yüksel. Thank you for attending and presenting.
Yes, thank you so much. I think it's on. All right, great. So it's my pleasure to introduce Professor Bengü Özuğur Uysal. I hope I pronounce this correctly. Professor Bengü completed a bachelor's degree in physics engineering from Istanbul Technical University in 2000. And she later on came back to Istanbul Technical University for a PhD in physics engineering. Afterwards, in 2012, when she completed her PhD, she started developing electrochromic and transparent conducting thin films with metal oxide nanoparticles. And afterwards, she started as an assistant professor at Kadir Has University, where she, among other things, established the Material Design and Innovation Laboratory. And this lab earned her 2 patents. I would like not to linger much more on the details, and please welcome Dr. Bengü at the stage here.
Okay. Okay, thank you very much for this nice invitation. I would like to thank Professor Can Anvarlıklı first, and this is a pleasure to be in here. And after discovered new thin films, of course, I just jump onto the polymer composites, and afterwards you can see the applications of the thin films. And actually, if you look at the literature and the flash memories and the vertical transistors, silicon labs, quantum phosphor, and silicon lasers, and so on. And my group actually produced the metal oxide thin films first, and the microstructural, optical, and electrical properties of them. And after that, the mechanical properties. And you can see that, yeah, thank you. Here, the electrochromics and the transparent conductive oxide materials, and with the addition of the aluminum, indium, and so on. And these are, typical shape of the structures when you look at the SEM images. And you can see all these characteristics of different metal oxide when you, skip down the, actually, all these periodic stable elements. And this is my second article when we are doing the PhD. You can see that the silica nanoparticle thin film structures and the changing properties of them, like the optical properties and the electronics also. And these are the methods for using, you can use these methods to produce the thin film materials. But for the silica, you can see those application areas. These are very different areas. Actually, if you add some vanadium oxide to your coating, you can see that the thermochromic materials, and also with the infrared radiation, we can easily switch out these electrodes, and you can see the optical waveguides or something else. And you can have different properties with the optical issues as well. And if you cover any silicon nanoparticle with the silver, actually you can have the antibacterial, anti-cancer properties. And I use always the sol gel process because it's a cost-effective method, and you can easily alter the properties of the material. And this is the first, in my PhD study, I generate this silica. First, I produce using the precursor TIOS, and I dissolve it in the ethanol. And after that, in the other beaker, you can see that the hydrochloric acid, the ionized water, and the ethanol. And from the second one to the first one, you mix these two beakers to get the silica salt. So this is the thin film salt, actually. And I produce in the Stober method as well. And you can use the ethanol as a solvent with POS again, but with the addition of the other things like this must be the distilled water, but it didn't see. Yeah. And after that, if you must add the water to this solution for the hydrolysis process of the second statement of the sol gel. And if you add the basic environment like the ammonia solution into that, you can have the nanosilica particles. And so for silica acidic environment, you can have the fibers or the thin films. If you want the nanostructure silica, you must add the base catalysis here. Instead of the HCl or another acidic environment, you need ammonia and the other basic environment to get the nanostructure materials. What I did is, as a thin film, you can see the wave structure on the surface if you look at these AFM images of the silica soil. And for the nanoparticle soil, you can have these after, of course, deposited using the spin coater machine. You can have this structure at the surface. And if you add these two with some proportional ratio, like for this one, 1:10, you can have the silica nanoparticles can be encapsulated inside the film. So it's actually good for us because you can easily control the size of the nanoparticles. If you just leave this nanostructure sol, after some time, you can see that these can be growing so fast. The particle size is, it will be increasing because of the Oswald ripening process. Because the larger particles can, eat the smaller particles, and you can have the high particle size at the end. So you need this structure to control the particle size that you need. So I tried different chemical compositions, like the ratios. You can see the change in the ratios with ammonia, so base catalyst to the precursor material. And you can see the difference in the sizes. So the 50 nanometer size, 80, and the 110 here. Of course, you need to confirm these structures with TEM as well to be published. All these matters needs more efficient solutions. And if you increase the temperature, you can see that the increase in the particle size a little bit, but after 1100 Celsius degrees, you can see the smaller particles with the crystal size actually, and you will see that the particle size will change. apparently. And these are the SEM images as well. You can see some agglomeration because these are not inside the silica film or something. So that's why there's no encapsulation here. And you can see that after some time, if you take this cross-sectional image of the SEM, you can see that there is an orientation of the nanoparticles. They want to, form the fiber after a while, and you can easily see that in the electrical, actually, components of the film, and electrical properties will alter. And these are the particle size distribution. These look like the Gaussian peaks after the AFM and SEM studies. And you can see that if you increase the amount of TOs, you can see that the lower the maximum diameters of the particle size. And you must, of course, confirm the crystalline structure. And the silica has the alpha cristobalite phase at this temperature. This is the high temperature, actually. And when you saw this broadband, you can say that it's from the substrate material, which is also silica. And these peaks refer to the diffraction of the Miller index of the planes for the alpha cristobalite crystal structure. So as you can see, the increase of the temperature gives 450 to 900 gives nothing because there is no phase change here. But after this temperature, you can see the sharp peaks, which are showing the alpha cristobalite phase. And you can see that the change in the full width of half maximum of these peaks as well when you change the ratio. So it can be referred to, it can be attributed to the change in the particle size, but this is the crystal size. These are different two things. And as you can see, the optical properties of the material as well, we will see in detail here. So as we go back to the basic physics, we need this physics, to actually eliminate something new always. So we are going back to electromagnetic wave. The electric field and the magnetic field is always propagational to each other, and the propagation of the wave is always proportional to these. So you can see that the angle between them is the right angle always. And you can see that the unpolarized incident beam with the Brewster angle going to the thin films, and it depends on the structure, it depends on the thickness of the films, layered films. And you can see that S-polarized reflected beams and the P-polarized transmitted beams. And these are, of course, these must obey the Fresnel equations like this for the magnetic part and the electric field part. And you can see that these reflectance and the transmittance is really correlated to the refractive index and these angles. As you can see, for the normal film structure, there can be the total reflection from the reflections of these plates and the film surface, and also there's a transmission from the film side and the substrate. As you can see, the total transmission when you just put your film into the UV visible spectrometer device. But if you have nanoparticle film, this can be different. So the previous equations will differ. Why is that? Because if you have nanoparticles inside it, you will have the reflection and both the scattering. So reflection consists of some of the reflection of the surface, and also it can consist of the scattering of these all of these particles, scattering from these particles, the small particles and the large particles and also for the transmission as well. So you need to reconsider the equation, and using the transfer matrix to put into the equation of this matrix gives us the multi-layer structure easily. Of course, after using the MATLAB program, you can have these approximation and the real part and the complex part of the refractive index. And the complex part gives us the absorption coefficient, and this part gives us the refractive index as well. And you can see that these are in the same trend, in the same page of the S and P polarization of the transmission response of the films. If you compare to the substrates, and these are the solid ones, as you can see, and these are thin films. How can we, recognize that? Because there is a wave shape, and it's still we can apply the Beer-Lambert's law, and also it's thin enough to apply the other, Fresnel equations. And if you put the nanostructure material inside the regular silica films, you can have the, more thick layer structure, and you can see these trends. And for the silica, we need to excite our material with the 280 nanometer fluorescence signal to get this emission. Actually, you can see these emissions of the silica, and there's a little change. There's a little shift between if you change the material's chemical actually composition. And what about the reflective index? There's a slight change between them if you change the particle size and for the extinction coefficient. And for the electromagnetic spectrum, as you know it, to form the absorption versus wavelength, you can have this actually as a basic. So when you give some photon to this medium, you can have the from one energy state to another state, you can have the excited electrons, and they are correlated with the energies, of course, and the energy difference must be h nu, the energy of the photon, and it can be the total of the electronic, vibrational, and the rotational energies. So for the electronic energy level, these are sharp, and the at the center of these absorption peaks, as you can see. But another moment like the molecular vibration modes we have. So we must add the, between the main energy levels, we have the other one to produce these lines actually around the center electronic energy levels. And FTIR can sense this using the infrared signal. And you can see that these are for the silica, and for different particle size, you can see a little shift of the infrared spectrum. And if you add the rotational energy levels, and you can have the UV visible spectrums, this, peaks with the absorption versus wavelength. It's like the, we can have the analogy to our eye. The spectroscopy can, work with the same trend as the eye, and you will be happy if you see this actually peaks. So there's a slight change, but after several experiments, we just have the same. So if you change a little, particle size a little bit, it's about 20 to 50 nanometer size. So you can see a slight change in the band gap shift, you can see. And afterwards, you will have the all these applications can be applied using these properties. Another one with the Imperial College, actually, the Miscanthus project, they want to produce the miscanthus plant silica-based silica nanoparticles, and as you can see, we need to check if there's silica of their miscanthus sample first, and afterwards the TGA, DTA analysis of them. As you can see, if you increase the temperature over 400, at least the 500 Celsius degrees, you can see nothing. So there's no yield between them. So you need to work out over 300 but below the 500 Celsius degrees to get the silica yield higher. And my group, actually at Imperial College, generated 5, and if you add this one from the biology department, 6 different ways to generate silica nanoparticles from the miscanthus. And these are some of them, of course, I can share in the article as well. And these are 2 reactions behind them. So you need to get the ash over 300 or lower temperatures for the sustainability. For this case, 300 Celsius degrees. And with the basic environment, and you need to get the sodium silicate first, and after that with the acidic environment you can have the silica nanoparticles with some salt, and after getting rid of the salt you can have the silica nanoparticles. And residue gives us the silica content, and you can easily improve using FTIR. Infrared can actually can sense the this silica bonding, stretching, and bending of silicon oxide. And after DLS particle size distribution, you can actually confirm the particle size using look at the PDI values. And with the, of course, UV visible spectrometer, you can have the absorbance versus wavelength at some nanometer wavelength. You can have some peaks. And we actually have comparing the silica structures, and as you can see, the 4th and the 5th phase of the extractions with different ways with the addition of the ethanol, you can see that there is no peak for the OH. That means there is no water inside it. We can easily get rid of water using this methodology, adding more ethanol into it. And the DLS results shows us the size distribution of the particles. So if you need the particle size smaller than 100, you need to add more basic environment to the system. And if you want to purify these nanoparticles, you can add more acidic environment, but it will increase the particle size. So it depends on what you need as an application. And TEUM results which confirm with the mapping, of course. These are the silica structures when you arrange the machine. And you can see the silica nanoparticles in size, and look at the range, which is 1 micrometer. That means that these are smaller than, some of them smaller than 100 nanometers. And after the TEM images, you can have the exact maybe particle size of these. And this is our winner for the actually we are applying these silicon nanoparticles for the knee. We are working with the hospital right now, so we need this one because it's easy to add the calcium inside it. And if you add the calcium, as you can see from the EDX measurements, the calcium's over there, then you can release this ion easily, and it can regenerate your knee if you implant this material with the bioglass. And these are showing the XRD peaks as well, which are showing us the calcium medium. And for the future directions, maybe they can use the silicon nanoparticles for the bouncy glass or the other applications. But here, as you can see, we just add this one, this disc, as a silicon nanoparticle bioglass here to, healing of the knee. And what else for the other metal oxides? So alumina can be, the ceramic material used in many places nowadays. And if you add these nano silica particles into this alumina structure, and then you can get the composite of them. And aluminum has another property actually. It can be, order the structure like the flower shape. As you can see that if you increase the TiO ratio of the solution, you can see the change of this flower shape and the increase in the particle size, and also the absorbance wavelength UV visible measurements can confirm that. And so when you increase this ratio, you can see the increase in the particle size and the increase in the particle size with temperature, and you can easily approve them using AFM, TEM, SEM, and XRD. Another one is another candidate is the titania. Actually, we are producing this with the Burkitt phase. These are, you can see, we change a little bit the water and the acetic acid ratio, that's it, to change the particle size for different applications. And if you add the alumina, you can see the flower shape as well. And it depends on its orientation as well. And the absorbance peaks and the band gap energies between the 3.4 to 3.72. And we can, of course, compare the structures between the XRD and AFM results. And Vanadia we prepared as the electrochromic films, and there's also the thermochromic applications for them before that. And we have actually vanadium dioxide here, not the pentoxide. It's really actually tough to disintegrate these two for this material using only the sol gel process. And these are, you can see the AFM images, the surface of the vanadia nanoparticles with different chemical composition. And as you can see, these are electrochromic materials. So you give some energy and you can see the bouncing back the energy as a response of the material. And you can see the change in the color of the films if you give some little voltage to the film. And you can see the change in the color. And this color is the intrinsic property of the material. So cyclic voltogram gives the results of them. And another candidate is the thin oxide. Thin oxide has the many applications for the solar cells, and you can use it as an, the base material or the actually for all these electronic applications as well. And you can have some type of different size of tin oxide and with different structures actually. And we only change the water content to precursor or the basic content to water, that's it. So it's easy actually. And for the zinc oxide, you can see the TEM images, SEM images, and if you change the dia surface reactant to water volume ratios and the absorption peaks change, you can see the band gap energy will change between 3.2 and 3.4, and these are for the aluminum doped zinc oxide, not the antimony dope. And aluminum doped tin oxide structures like the squares over there, and fluorine doped structures, tin oxide. And you can easily compare the TEM images of ISO and the aluminum doped zinc oxide. And as you can see, the diffraction pattern of this is very small when you compare to this one. So this is 100 nanometer scale, and this is 50 nanometer scale. So the band gap will change. And if you add some molybdenum, it can be, you know, alter everything as a properties. And for the, you know, addition of the chrome, molybdenum oxide, vanadium, zinc, and chrome sulfur, and so on. So at least you can have the hexagonal shape nanotubes-like structures. So if you can see, using these different type of metal oxides, if you have this layer structure, you can have these properties. You can change easily the color with giving a little bit of the voltage, as you can see. So from 1 minute to 40 minutes, you can see the change in color. And if you need to, you know, get this, you need to confirm that the cyclability of the material using the UV visible spectrometer as well, and the XPX as well, of course. And another actually measurements for using the TMDs. TMDs are consisting of transparent materials with the sulfur and the selenite of them. It can be the molybdenum, tungsten, and so on. And this can be the sulfur or selenite element of this structure. And these will start at these dates, actually, 209. And you can see the usage of them. There are plenty, actually, applications for them. You can see the mechanical properties will getting better, and also because of this shape, these are looking like the graphene structure. So if you use graphene as a, you know, template, and instead of this, you can use the molybdenum sulfide and tungsten as well for the photovoltaic application, and the other applications in also the photonics or the and the optoelectronic applications. You can use the molybdenum selenide. And if you add these into these are the semiconductor materials, as you can see, between 1.2 electron volt to 1.4 electron volts, and this is the range for the band gap energy. And if you add these materials to the polymers, you can have the polymer composites with these huge, you know, plenty application area. Actually, my group using the polyacrylamides because these are more, you know, sustainable material. We use the polyacrylamides in our, you know, baby diapers and everywhere, actually. It can easily swell, and then as you can see, the compression loads can give addition of the graphene oxide. First, you know that the graphene oxide is a trend, but afterwards you can see that the TMDs and transition metal dechalcogenides are the trend right now. So the conductivity will change, of course, and this is the route to produce the polyacrylamide. We need an acrylamide, of course, bisacrylamide as a crosslinker. If you add the initiator APS to the material, you can see that the reaction will start, and addition of the TEMET, which is the catalysis element, and you can have the polyacrylamide structure in the, you know, transparent form, and afterwards you can see that it can be glass if you dry it. And actually, this is the biomimetic point of view of the structure. You can see the this seashell, mother of pearl, shows the same with these tablets. Between them, they have the organic material. So we need to add the PVP instead of the organic material, and our inorganic material is the polyacrylamide, and the main material is polyacrylamide, and the addition of the TMDs, you can see with the different amounts of the TMDs change its color. And For the characterization, UV visible measurements shows us the transmittance versus time. Time is important for us. Why is that instead of the wavelength? Because you can see that the gel point. So for this phase, our material is liquid, and for this phase, our material is in the gel form. So phase transitions are important, and when you see the phase transition, you need to see these sigmoidal peaks. So the second derivative can give this gel points. And if you increase the content of the TMDs, you can see the change in the transmission of the relative, which is given us, the change in the transmittance intensity if you normalize the transmittance intensity. And as you can see, the decrease in the transmittance if you increase the content because of the structure shows us like the gray powder or something. So you have the transparent polacrylamide. If you add more, you can see that it turns out to black. And after the addition of them, you can easily calculate sometimes it can be tough, of course, to find out the gel point between these two. So this is one state and this is another state, and these are for the scattering plots. For the another measurements, actually you have to use another machine to get this. And you can see that these are obeying the Boltzmann equation, which is the sigmoidal equation. And gel points will increase if you increase the amount of the TMDs. And let's skip these. You can have more information using these plots for the structure. And the same for the molybdenum selenide after molybdenum sulfide and the tungsten versions of them. You can see the band gap shift a little bit as well. And we can apply the Beer-Lambert's law. We can still apply because we are thicker than 100 nanometers. So the thickness is important to apply this law, Taux relation. And the absorption coefficients, extrapolation of them gives us the band gap energy. Of course, this is the optical band gap. You need to confirm that band gap trend with the electrical measurements as well. And what about the mechanical properties? Literature says that the mechanical properties are better if you add more. Then you can easily approve that using the compressive load here versus compressive extension plots and stress strain curves. You can calculate the Young modulus, compare here. And there's always critical point for the TMD amount. We always see that. And for this point, before this point, there's a decrease, and after that, there's an increase. So there's a threshold point for the tungsten disulfide and all these TMD amounts. If you need to get the more strengthened, then you must add more TMD to your structure, but you have to get rid of these transparent material. So I already said that. So the metal oxide nanoparticles were prepared using sol gel technique, and it can be controlled. All these properties can be controlled by the chemical content, and also the if you add the TMDs into the polymers, you can have the nanofiller ratio can change everything in the solution, like the mechanical, optical, and the electronic properties of the material, and band gap energy values as well. And if you look at the trends, so the thin films composed of metal oxide nanoparticles have become essential in photonics. nowadays you can see these to 2023 article here. You can see the silica mesophorous thin films using plasmonic nanoantennas. As you can see, delta T over T values can have the cyclability value versus time. And another one, which is so recent, October 10, here 11 days before. So these can be with using of the vanadium with the, you can see that the oxygen with 2 amount. So this is so important because it's easy to generate the pentoxide of vanadium oxide, but you cannot have the VO2 structure easily. This is so hard. If you want to use the sol gel process, it's so hard. But if you can do this, you can easily modulate this signal. You need a pump pulse, always like driving force a little bit to get this oriented structure actually for these plasmonic applications as well. And what are the role in photonic systems of these metal oxide thin films? Enhancing light matter interactions for better device performance. If you change the nanoparticles size, you can easily change the optical properties. So there's always, win-win situation. Improvements in sensitivity, efficiency, and the functionality. And there are many applications can be for the photonics applications, of course. And the optical properties, you can see that the reflective index can be tunable, high transparency in the visible regions, and also you need to get in the infrared regions to confirm that. And non-linearity enables the advanced photonic functionalities. And if you integrate these metal oxide films, this is the, so trend right now with the polymer composites, then you can see that the mechanical properties will change as well. So the polymers gives us the flexibility. If you integrate the metal oxide films into it, then you can easily tune the optical properties, alter them. And advanced optical sensors and the flexible photonic devices can be the application areas. And these are the future prospects of this medium and innovations in quantum photonics and emerging fields. So you need to confirm that it's for the quantum photonics, of course, you need to decrease to the, go down to the particle size as well, and to get the quantum dots. And potential high speed, low energy, miniaturized photonic systems you can have. And one actually research group can have these miniaturized photonic systems, and it can easy to compute the system using AI right now, and expanding the capabilities of photonic devices using the metal oxide thin films. And this is the other recent actually article using the perovskite materials. Maybe you want to, I will share all these presentation. Maybe you want to look at this as well. So this is my group from Kadras University, Imperial Reis collaborator, and this is the Imperial group when here, and thank you.
Thank you very much for this very educational talk with lots of experimental data, a very impressive amount of experimental data. I would like to give you and this is for we decided that you will give donation to our students. So thank you very much.
Thank you very much. Is there any question? By the way? No?
Any questions from the audience?
I just remember.
Then we will go to the next speaker. Our next speaker is Dr. Yiğit Ozan Aydın. He holds a bachelor degree in physics and afterwards did his master in micro and nanotechnology from Metu University. He later on went to Canada to the Center for Optics, Photonics and Lasers, and received there his PhD. Also in Canada, he is now, I mean, not exactly now, but he still works, let's say, between Turkey and Canada, and worked not only in academia, but also has worked in two companies, Femton in Canada and Fiberlast from Turkey. Between all this, he also still found the time to make I own 2 patents and generate a lot of scientific literature. So I would please like to welcome Yiğit Ozan to the stage. Then please, whenever you are ready, feel free to start.
Sure. Thank you so much, first of all, for inviting me to this wonderful event. I'm happy to present the work that I have been involved over the last 7-8 years. And today my presentation will cover the 3 micron fiber lasers, high power fiber lasers operating near 3 micron. And first I will discuss why this topic has garnered significant time, investment, and the attention in recent years. And as well as I will show you the advancements that we made in last 7-8 years and the challenges we have faced along the way also. So a couple of years after the first laser invented by Mayman by using a ruby crystal, Elliot Snitzer was the guy who showed the first optical modes. And then after, the same person showed the fiber laser demonstration for the first time. And then later, David Payne from University of Southampton showed the first erbium doped fiber amplifier. It was kind of a milestone. Another milestone, just a couple of years after, was made by Snitzer again. He showed the first double-clad fiber in the history. So it was important because this kind of fibers just increase the maximum output power achieved from this kind of systems. And then, not surprisingly, a couple of years after, Gapontsev just showed the watt-level laser for the first time. So this barrier broken in 1990. And he showed a 3.9 watt erbium doped fiber amplifier. And this guy became one of the richest person in the world after this invention, because he just found a company called IPG Photonics, probably like most of you know it. And then the evolution of the output power of such lasers continued. Here in this graph, you will see there's a kind of logarithmic increase for the average output power from the nearly diffraction limited beams, starting from 90s, from a couple of watts till 2014, the output power reached more than 10 kilowatts. So, but after 2013, there was a limitation, which is called mode instabilities, which limit the fiber laser output for the nearly diffraction limited beams. So this is kind of limits, which just limits the maximum average power can be taken from a fiber component. So, but companies, industrial side, continue to increase their output power by using multimode laser. For instance, in 2013, IPG Photonics just demonstrated a 100 kilowatt laser. And a couple of months ago, a Chinese company called BWT showed a 200 kilowatt fiber laser. And the next year, Lockheed Martin is planning to deliver a 300 kilowatt fiber laser to US Army. So as you can see, there's always a trend to go to higher and higher output power. So, but where does it come from? Actually, as probably you all know, it comes from the different kind of applications. If you check the 1 micron region, it's this kind of lasers are pretty popular for cutting, marking, and welding. And also, they are very good to create complex 3D structures, so additive manufacturing. And on the other hand, for the defense and aerospace, these lasers are pretty good because their output power are reaching a couple of hundred kilowatts of output. Because of that reason, they can be used for range finding, target designation, or directed energy weapons. But if you just go to 1.5 micron, this is the telecommunication wavelength. It's the because like internet is coming to your home or office is like if based on the fiber technology, the laser inside is erbium doped fiber amplifier based on 1.5 micron. And this wavelength is eye safe. Because of that reason, it's very good to use in LiDAR application, especially the long distance LiDAR applications. Since it's eye safe, we can use the same laser for the eye surgery if you have the femtosecond version of this laser. If you go a little further to 2 micron, for instance, the 2 micron is like very interesting wavelength because it's well absorbed by the water and the biological tissues. It's because of that reason, this wavelength is very ideal for medical procedures like soft tissue cutting, ablation of the tissue, or lithotripsy. This kind of applications are pretty good for using this kind of laser. And then gas sensing is another application that we can use 2 micron because there are some important gases located around 2 micron. And on the other hand, these lasers, 2 micron lasers, can be used to generate supercontinuum till like 5, 6, 7 micron. Because of that reason, they are very good scientific tools to generate supercontinuum and use these supercontinuum sources in spectroscopic applications. So if you check the high power laser sources based on the wavelength, the maximum output powers for each wavelength is like has a kind of trend, like as you can see here, like very usual. This is like published demonstration of lasers as a function of emitted wavelength. And this trend is coming because if you want to just generate, let's say 2 micron laser, you always rely on the lower output power because you need to populate your ions to the upper level. So by using a shorter wavelength, because of that reason, this trend is like pretty normal. But in this presentation, I will focus on this region, 3 micron region, and I will try to explain what kind of challenges we had and what did we achieve actually in last couple of years. So if you check the same trend, like as the other lasers, the power evolution of the 3 micron lasers starting from 90s also has kind of logarithmic increase, as you can see from this graph. So, and it means that there is always a growing interest in scaling of 3 micron lasers also. So as you guess, these interests come from 3 main applications. One of them is defense, spectroscopy, the other one, and the last is the medical. So I will explain step by step for each application. Let me start with the defense. Here you will see the transmission spectrum of the atmosphere. As you notice, there's a very high transmission around 3 micron region. Because of that reason, this kind of lasers could be used in monitoring and the tracking of the aerospace vehicles. On the other hand, we know that the thermal signature of blackbody emission of many aerospace vehicles located between 3 to 5 micron. Since this is a like very good advantage for using this kind of laser for countermeasure applications, for instance. Another application is a spectroscopy. So in general, the tunable systems already have been demonstrated for covering 2.5 micron to 5 micron in order to detect the important gases. Here in this graph, you see the absorption line strength of some of the important gases located in this region. And then these tunable systems are based, like if you have a tunable system like near 3 micron, you could just detect like a couple of gases, acetylene, hydrogen cyanide, ammonia, methane. These are like a couple of gases that you can detect. But on the other hand, these lasers can be used again to generate supercontinuum source and replace the optical parametric generators in the future. And the last application I would like to talk, and I guess it's the most important one for me, is the medicine. So as a human being, we are consisting of lots of water, 70% or more, depending on the tissue type. The amount of water could go like up to 80, 85%. So here in this graph, you will see the water absorption spectrum, and you will notice the peak around 3 micron. So this peak is like very important for us, because if you have a laser which is absorbed almost 10,000 times more than a laser wavelength around 1 micron, you could use it in many different kind of medical applications like microsurgery, skin treatment, dentistry, and bone repair. So, I will show you a little video about how the systems are working. So in this video, you see a kind of fiber tip here. This is the fiber tip, 200 micron fiber tip, which is covered by a coating. So, and then if you just choose the right parameters to process a tissue, you will get like very good results without any damage by using just 3 micron wavelength. So I will come back to this video and I will show you other videos about the potential of these lasers. And in this video, you see like a 200 micron fiber goes into the brain and then just make a cold ablation, just evaporate everything without giving any damage. So this video was taken by Light Matter Interaction Company located in Toronto. They are focusing on this kind of medical application based on 2 or 3 micron fiber laser sources. So in this part of presentation, first I will show you how to build a 3 micron laser. I guess this is like, there's no difference than other lasers, but there are like slight differences I would like to show you before showing you the contributions that we made. So basically there is no difference than building any other free space solid state laser. Just instead of using a crystal, we are using fiber as a gain medium. And then one of the good advantage for using a fiber laser is you can just make it simpler. Instead of using free space components, you can add fiber back gratings. And then it makes it like monolithic. And you don't need the alignment if you have this kind of like a simple system instead of using a system that which requires always alignment. So, and then if you want to just build from scratch a fiber laser operating at 3 micron at high power, so like there is no difference than building another system for the requirements. Actually, what we require is we need fiber components, a dopant that we have to choose, a pump wavelength, and also we have to understand what's going on with the chemistry and the physics. So let me explain step by step first. So for the fibers, actually, to build a 3 micron laser, we need a fiber which transmits 3 micron. So in this graph, you will see the transmission wavelength, transmission capacities of the different kind of fibers. Here you see the silica fiber, which is the most popular fiber, which transmits up to 2.1 micron. Even with the low OH fiber, you can just transmit up to 2.1 micron or maybe 2.2 micron. But on the other hand, there are other fibers like Ziblan, tellurium oxide, and indium fluoride. You can go up to 7-8 micron transmission. Here, there are like many options, but in general, we are choosing Ziblan fiber as a kind of a gain medium and also the transmission medium. The reason for that is the tellurium oxide, indium fluoride, and other 2 fibers are pretty good actually for the transmission, but the fabrication process is pretty difficult. Because of that reason, Ziblan looks like a very good candidate for us. And in this presentation, I will say either Ziblan or fluoride. Sorry for that. Like the 2 of them are like same meaning. It's coming from the compounds, the first letter of the compounds, and then the highest compound is the fluoride-based zirconium fluoride. Because of that reason, we also call these fibers fluoride fibers instead of Ziblan. So here in this graph, you will see the estimated non-relative decay rate at the room temperature for the silica and the Ziblan fiber. You will notice that there's 100 times, there's 100 times difference in the decay rates, and it gives this kind of transmission property of 3 micron into the Ziblan fiber compared to silica. So, and another thing is of course, the fiber components that you have to build and develop different kind of components, like the splices, end caps, and different kind of splices and like combiners. To make this kind of components, in general, people just remember the arc splicing. It's like a very basic process, like everybody knows. 2 fibers are getting together. You're just using 2 electrodes and then apply a current to these electrodes. Electrodes gives an arc and 2 fiber gets together. So, but the process is not that easy with the Ziblan fibers actually, because Ziblan fibers transition temperature is pretty low compared to silica. Silica fibers has a melting temperature more than sometimes 1000 Celsius. On the other hand, the Ziblan fibers has transition temperatures around 300 Celsius. Because of that reason, we have to find a new method. Like instead of using arc splicing, we use in general filament-based splicing. So there is an omega-shaped filament based on iridium or graphene. And then it's like the same process. Instead of using arc, the 2 fibers are coming together, and we apply just a little bit of heat. And we have to be very careful while applying this heat, because the room between the melting and the transition temperature is already like 60 Celsius. So it requires like a very precise, very precise procedure. So, and the other thing that we have to be careful about choosing the dopant if you want to make a very high power fiber laser at 3 micron. So the one of the dopant here is the dysprosium. I would like to explain first the dysprosium. It's like very ideal to generate 3 micron. In this graph, you will see it covers an emission band starting from 2.6 micron to 3.4 micron. It's perfect to generate longer wavelength, longer than 3 micron. But one of the disadvantage here, you see the pump wavelength for the like same state that you get the laser. It's like in-band pumping. It's just already like the pretty much close to 3 micron. So because of that reason, it's already very difficult to build a laser at 2.8 micron to generate 3 micron. This ion is not ideal for generating high power emission at 3 micron. The other wavelengths that we can go higher energy levels are also not easy to find. You have to build a laser instead of buying just a diode and pump your laser and get the wavelength you want. So if you just check the holmium, this is another popular ion people are using to generate 3 micron lasers. It has a very nice emission around 2.94. Like this is the very close to absorption band of the water, especially for the medical applications. Laser built by this ion is like very good actually. But again, there's a problem with the holmium. Very high power, the efficiency is like pretty low. This is coming because if you want to generate a 2.8 micron between these two levels of the energy diagram of the holmium, you have to pump your system by using either 1150 nanometer. This wavelength is not very common. You have to build a Raman laser, or you can go and pump it to 890, but you will have some temperature issues, some mouth-phonon relaxations coming from this level. And if you check here, the lifetime of the upper state level of the here is shorter than the lifetime of the lower state level. Because of that reason, there's a bottleneck effect, and we have to add another ion to just remove this bottleneck effect. And the fiber fabrication process is not easy in this kind of using in this kind of ion. So, and another one is the erbium. Erbium is like very common wavelength for 1.5 micron, as you all know. And then to generate 3 micron inside of a fluoride-based fiber, you just pump with 980 and you get 3 micron. And there are already like problems that I will explain you later. But the good thing is the pump wavelength that we use is 980. This wavelength is like pretty common in telecommunication, that you can just build a 1.5 micron laser by using this wavelength. Erbium has absorption, and at the same time, it's good for ytterbium lasers. Because of that reason, the market for this kind of diode is very good. You can find different kind of diodes, even like slightly wavelength shifted diodes operating near 980. And then the money you spend for this kind of diode is pretty low compared to other wavelengths. So because of that reason, we choose the erbium as a like nice ion dopant to use in our fiber to get 3 micron. So let's discuss the physics and chemistry. This is the erbium doped Zibland fiber energy levels. Everything is going between these two levels. But as you see here, there's a problem again. It's the bottleneck effect. The lifetime is shorter than the lifetime of the lower level. So, and at the same time, another problem is waiting us. This is the excited state absorption located in this level. Once you populate your ions to the upper level, some of them goes to like the further level, like so then they come back and they create some heat. And it's not efficient or also for the population inversion. And another energy transfer upconversion located in this level, which depopulates the ions from this lasing level. And another problem is the cross relaxations. One of them is coming from ground states and populate this level. This is also, again, not good for the population inversion. So, but the good thing is we have energy transfer upconversion in this level. That's perfect for us because it depopulates the lower level and populates the upper level at the same time. But the question is how we get like higher energy transfer upconversion. The higher energy transfer upconversion is like actually the increasing the ion-ion interaction. To get higher ETU, we need high ions. It means we need high doping concentration in our fiber. So if we have high enough doping concentration, we can get high ETU and the high efficiency. But at the same time, the basic problem is the high concentration means always high temperature in fiber lasers. Because of that reason, we have to well adjust the cladding core and clad ratio of these fibers. And also we have to make a very good polymer engineering. So now we have everything. You have, you know everything about the 3 micron fiber laser, high power fiber lasers. So let's think about, we have a cavity and we have our highly doped erbium doped Zibland fiber, and we are pumping with 980 and we get 3 micron. But it's lased, but it's not lasing very long time. The reason for that is if you check the literature and try to find a kind of 3 micron fiber laser operating at high power, you will see always a fiber tip degradation problem. There is no laser operating like hundreds of hours in this kind of wavelength. So basically the reason for this is because of the OH molecules in the air actually. So we know there's a water on the air. And the direct consequence is coming from the OH absorption band, which is like matching at the 3 micron. And also the nature of the fluoride-based glass is the hygroscopic. And once the OH or the water comes into the structure of the fiber, the glass continues to dissolve, and water penetrates the matrix, and the crystal grows at the surface. So this is a problem we need to solve to get like long-term operation of this laser. But to solve or reduce this effect, we use end caps. We use another fluoride-based fiber or different kind of fibers, which I will explain you later, and which has a core diameter bigger than the core diameter of our fiber system, which just reduces the amount of heat on the surface. And then we can just increase the operational time of this system by using this method. So I would like to now, you know everything pretty much about this kind of system. And now I will show you which kind of contributions we made in this kind of systems recent years. And I will just show you the parameters, like the key parameters of this system. Let's think about, I came to your office and I just tried to sell you a laser operating at 3 micron. And one of the basic questions you will ask me is if the efficiency is good, because nobody wants to operate a chiller or like something which makes a lot of noise and you need to spend a lot of money for the electricity. You will ask me the efficiency. And then if it is pulse, of course, the pulse energy. If it is CW, you will ask me the output power. This is like basic parameters of the laser. And then you will tell me, oh, one of the guys from University of Toronto told us these lasers are not good for long-term operation. Do you have any solutions for that? And then, yeah, and I guess I will tell you, don't worry, we have record efficiency, pulse energy, and output power that we achieved during the last couple of years. And also we solved this long-term operation of these lasers. And I will just tell you step by step what we did for each application, each parameter. So let me start with the efficiency. So efficiency is like very critical components. And if you just check the 2.8 micron emission between those two levels and pumping with 980, if you make it like quick calculation, it's the quantum defect, which is around 35%. 0.98 over 2.8 micron will give you the 35% limit for the Stokes limit. So this is not bad efficiency for a fiber laser, but still we just try to understand if there is a way to increase the efficiency more, because we know there's 1.6 micron that we can emit from the same erbium doped fiber. And because of that reason, we just try to make a cascade experiment by using a piece of fiber. We injected this piece of fiber, our pump source 980, and we try to generate 2.8 and 1.6 micron together, as you can see from this graph. It's like basically you just one photon, you just go and populate this photon and you generate two photons at the same time. This is called cascade lasing. So for these purposes, we just built a very simple cavity, which is based on a piece of fiber and pump with 980. And as a input coupler, we use highly refractive dichroic mirror. And at the end, we use a 4% Fresnel. And we expect to see 2.8 and 1.6 micron together. And we change the length of the fiber to see what's going on if we change the length of the fiber first. So here in this graph, you will see the red dots represent 2.8 micron. The black ones represent 1.6 micron. So here from 3 meter to 10 meter, the first thing we notice is the total efficiency is increased. This is something we're expecting because we increase the length of the fiber, the absorption is increasing, and also the threshold of each laser is getting lower, and then we get higher efficiency. But interestingly, we already exceed the stock limit at 2.8 micron, which was 35%, once we use 10 meter fiber. And as you notice, the efficiency of 1.6 micron is getting lower and lower. So, and then we just wanted to go and build another laser, well optimized. So how we can build this? First, we can increase the length of the fiber to absorb all the pump power we are providing for this cavity. Because of that reason, we just increase the length of the fiber to 21 meter. And then it gives us more than 90% of pump absorption. And then we just add a fiber Bragg rating at the end of the system operating at 1.6 micron in order to keep all the 1.6 micron inside of the cavity to see the real effect. And the reflectivity of this cavity, fiber Bragg rating is almost 100%. And lastly, what we did is we add another fiber Bragg rating in the beginning at 2.8 micron. This helps us to reduce the threshold of the lasing at 2.8 micron. So at the end, we got almost 50% efficiency at 2.8 micron. And this is the highest efficiency that is achieved from a 3 micron fiber laser. And then where it comes from, actually, we just discovered a new excited state absorption inside of fluoride glass fiber doped with the erbium. So we made a very simple pump probe experiment based on supercontinuum source and a pump diode. We just got a piece of fiber and pump it with 980 and add a supercontinuum from the core of the fiber. And then we checked what's going on if you increase the pump power. As you can see, the new discovered excited state absorption is located very close to 1.7. And in the energy level, it's located here. So it's what's going on is like once you pump your wavelength, you generate two wavelength, 2.8 and 1.6 micron. And one of the 1.6 micron ion goes to the upper level by this excited absorption and recontribute into the lasing process and gives us 50% efficiency. So the pulse energy is a very important topic for our lasers because people are pushing the output power of such lasers for the medical applications. Here in this figure, you will see what's going on if you use a surgical scalpel in the operation, the medical operation. So it will create a kind of shock waves for first of all, and which I don't show here, and also it will create a tearing of the tissue and it will create some shear. It's not a perfect tool. It's perfect tool for now, but maybe in the future it won't be a perfect tool because we know that if you just reduce the duration of the pulses shorter than the thermal relaxation time, which is around 1 nanosecond to 5 nanoseconds for the biological materials, and also if the duration is shorter than the thermoelastic stress propagation time, if you can get like a cold ablation result, as I show you in the first part of my presentation. And let's think about you have pulses little longer than the 10 nanosecond. It will create again the shock waves and it will create some damage zone. But if you just use the pulses shorter than 10 nanosecond, maybe it's good to use like 1 nanosecond to a couple of hundred picosecond. You will get like just vaporization of the tissue because of the dynamics. But you can ask me what's going on if you just use pulses shorter than 10 picosecond, let's say, or femtosecond pulses. The answer is it creates plasma. It creates like high energy electrons on the surface of the tissue. So it can be like very, it can affect the tissue and you can get like cancer cells. It can mutate the formation of the tissue in the long term. Because of that reason, for the magic number for us is like a couple of nanosecond or a couple of hundred picosecond for this kind of operation. I will show you two videos to just well represent my figure. Here in this first video, you will see a vocal cord surgery, which is made by carbon dioxide laser. You notice like it's very clear that there are like heating zone. It creates some heat. But if you just use the 2.8 micron picosecond laser, which is like 700 picosecond laser, I guess, you can get like very clear results without any damage on the same tissue, on the same vocal cord surgery. So the key is like choosing the correct parameters of this laser. This laser can open like new doors in the medical applications. So in the second video, you will see an egg membrane. So this is an egg yolk, but there's a membrane on it, as we like to just make it like more clear. They put a dye, and as you can see, the egg membrane can be just taken by using 2.8 micron laser without cooking it. So it means because it's just evaporating, it's like an effect, like a very interesting effect. Just we can evaporate like a couple of micron thickness of egg membrane and take it from the egg yolk. So now you saw the potential of such lasers, and also I would like to show you like what we did to increase the performance of such pulse laser systems. So basically these systems are like making with the fiber, it's like pretty difficult. Because of that reason, we just use the combination of the solid state technology and the fiber technology. Solid state technology is already robust, but the output power of this technology is like very limited. Here you will see a very simple OPG, optical parametric generator, made by light matter interaction. So here you see the $1 Canadian. You can notice like it's very compact system. And what we did is just use this as a seed and try to increase the output pulse energy of this system by using a piece of fiber and amplify the signal inside of this fiber. So basically the best ion for this is the erbium and again the holmium, because they have a very good emission around 2.9 micron, where the water is absorbed very well. And then there are already like different kind of works made before us and after us also. They show it's possible to get like almost 80 microjoule output power at 840 milliwatts and with 24 picoseconds. This is a very ideal system, but the average power is like pretty low. And then some of the groups, like one of the group achieved 4.2 watt. It's very good average power, but their pulse energy was like way longer for the medical applications. And then we already like in 2018 achieved 2.45 watt, 45 watt. and 500 picosecond pulses with almost like around 100 microjoule pulse energy. It was a very good system, but if you check, it's like pretty complicated because you have to pump from free space, and long-term operation of the system was not quite good. And another group after us show more than 5.5 millijoule pulses with 10 nanosecond. That's perfect parameter for medical application. However, the average power was like only 7 milliwatt. So considering all the challenges that we had before, we just built another system, another amplifier based on optical parametric amplifier as a seed. So an optical parametric amplifier used as a seed, and we used 2 fiber stages and increased the power of the optical parametric amplifier provided by Light Matter Interaction Company. So I will explain step by step. So first of all, a 7 microjoule of pulse energy at 2.79 micron injected into the fiber. The pulse duration is around 1 nanosecond, maybe a little less than 1 nanosecond. And we injected into a 5 micron core size fiber, and they amplified up to 0.5 millijoule already by using only just one stage of amplifier. And our average power is more than 2.5 watt. So here is the key difference from the other systems. And we used for the first time a fluoride-based combiner. It's a fuseless side pump combiner based on the tapering of the silica fiber, as you can see from here. And then another difference is the core size of this fiber that we use is like very special, 85 micron, highly multimode. And this fiber was fabricated just for this experiment. And it was very easy after that to get more than 2.5 watt power. So then we built another amplification stage, but in order to protect this stage from the back reflection from the parasitic lasing, we had an isolator. And the seeding power coming from the first stage is injected into the second stage. And the second stage also pumped from both sides by using the combiner that we developed. And at the end, we got 5.1 watt, 1 millijoule pulses at 2.8 micron wavelength. This is the highest pulse energy achieved from a fiber laser system operating around 3 micron. So, and this is the spectrum of the system at 1 millijoule. As you can see, it has a peak around 2.8 micron. And this is the pulse duration of the system. We have around 700 picosecond pulses. And this is the pulse chain. It's like pretty stable system. So, and the other parameter is the output power. Output power is the key parameter for especially some of the medical applications also, but the defense industry. And let's go back to the energy diagram. We have ground state absorption, we have 3 micron, and you remember we have ETU here, which helps us to get like higher efficiency and depopulate this level. So it's good to have this ETU, but to increase this ETU, we have to dope the fiber more. It creates some heat. And it's good also to have this ETU, high doping concentration, because high doping concentration means it's short length of fiber. These fibers are pretty expensive, and using short length of fiber is always good. So because of this heat problem, is a common approach to build a CW laser at 3 micron is, and probably it's 1 micron also, lasers are built in this technique, is build a fiber Bragg grating inside, right, the fiber Bragg grating inside of the passive fiber first, and then splice this one into an active fiber to reduce the heating. But the splicing process is like pretty challenging in Zibland fibers, as I mentioned before. It creates some, first of all, there's no like 100% transmission splice. So because of that reason, this scattered light goes into the polymer, fluoroacrylic polymer on the fiber, and then it creates heat. Polymer is absorbing more than, I guess, 10,000 times more than what it absorbs at 1 micron compared to 3 micron. So this is one of the basic problems. And another one is, as I said, it's a challenging process, and each splice creates round trip losses in the cavity. So because of these challenges, we just wrote the fiber Bragg grating inside of the active fiber. So, and because it's on the active fiber, we will have the heat problem. Instead of solving this problem by using like very good cooling systems, we went back to the energy diagram and we tried to just cheat a little bit. So if you check the energy diagram again, exact state absorption in this level was the real responsible thing for generating heat, because your photons are going to the upper level. With the multi-photon relaxations, they are coming back and they generate heat. But if you check the cross-section for the ground state absorption and the exact state absorption together, you will notice that this exact state absorption is getting lower if you just shift your wavelength a little bit longer than 980, like, for example, 982. We already tested this. We just took a piece of fiber and the pump this fiber at different kind of pump wavelength, starting from 970 and up to 982. As you can see, the temperature increase here is the red dots is like it's increasing all the time. Once you come to 980, 982 region, the increasing of the temperature stops. That's basically because we are limiting the excited state absorption, because compared to ground state absorption, it becomes pretty low. So, and basically using this advantage of the energy diagram, we just use shifted wavelength diodes operating around 982. Another thing is we just use optimized fiber Bragg ratings. So the fiber Bragg ratings, basically, we are building our fiber Bragg ratings by using 800 nanometer femtosecond laser. And then these lasers, they basically, the length of the fiber Bragg rating is pretty important for the high refractive fiber Bragg rating, because what we do is we are annealing this fiber Bragg rating after the fabrication process to make sure that they will survive at high temperature conditions. Actually, the high temperature conditions for fluoride fiber is around 100, 150 Celsius. So because of that reason, we just keep the length of the fiber Bragg rating long for the high refractive fiber Bragg rating, and then anneal it at 150 Celsius. And then we do the same thing for the low refractive fiber Bragg rating, but since its length is pretty short compared to high refractive one, the efficiency, the refractivity is reducing. This is what we want. So what we choose is 8% reflectivity at the end for the cavity and almost 100% reflectivity for the beginning of the cavity. So, and then another thing what we did is we pumped the system from the both ends. Instead of pumping from the one side, we pump from the both end. 80% of the pump is used from one side, 20% of the pump launched from the other side. And we protect the fiber face by using an end cap, which is an aluminum fluoride end cap. And then at the end, we got almost 42 watt output power with 23% efficiency. And this is the highest power achieved so far from fiber laser cavity operating at 3 micron. And here you see the wavelength of the cavity is around 28, 25 nanometer. So, but as I mentioned, we had a fiber tip degradation problem. So the system didn't survive that much. If I remember correct, it was like a couple of maybe seconds. Later, the systems failed. And also we did the same test at 20 watts and we observed the same problem, but the only difference is the system just survived a little more. So, and then in this part of my presentation, I would like to show you what kind of solutions we offered for this OH degradation problem. So remember the last system at 40 watt, we just operated this system at 20 watt. And at 20 watt, the system is working perfectly. And has a RMS the deviation of the RMS is like around 0.5%, and it has an efficiency of 23%. So this system, as you can see, we say it's operated at 100 hours, but we found different kind of end caps to protect the fiber face. And then this is why actually the system is operated till 100 hours. And what we did is like, we just add a zirconium fluoride fiber at the end of the system. And we just add different kind of end caps and check the temperature of these end caps at long-term operation, in long-term operation. So first, what we tried is the fluoride-based fibers as an end cap, like 200 micron core size fluoride-based 2 fibers. One of them is zirconium fluoride, the other one is aluminum fluoride. And also we tried the oxide-based fibers for the first time, like germanium oxide and silica fiber. And also we tried the sapphire fiber as an end cap material. And then here you will see the image. These lengths are around 500 micron. For silica, it's 100 micron length. This is the laser at the end of laser cavity, and then these are the end caps. And also we use the thermal conduction cooling to limit the maximum end cap temperature by using a copper plate. And we start our experiment with aluminum fluoride and zirconium fluoride fiber. As you can see at 20 watt output power, zirconium fluoride fiber is failing. In like a couple of minutes, I guess it's like in a very short time. But on the other hand, if you use aluminum fluoride fiber, the system is operating up to 9 hours and then temperature is increasing and this fiber also fails. But the good thing is we can use this kind of fibers in low output powers. Like the system sometimes we build operating around a couple of 100 milliwatt, and this kind of fibers are good because they have also low refractive index. It means there's not that much of parasitic lasing going on. But the problem is high degradation rate. Maybe they are not ideal to use in a couple of 10 watts of system. And then we just tested germanium oxide fibers from 2 different companies. And as you can see, they survive up to 100 hours without any problem. But they have a temperature, the trend where the temperature is increasing, like almost more than 100 Celsius for one of them. So, and also if you calculate, if you just make a trend at 100 watt, the beginning of the temperature in the beginning will be already reaching almost 200 Celsius. Considering the degradation, transition temperature of the zipline is already 260 Celsius. It's like pretty dangerous for the future to use this kind of system. And also another disadvantage of this germanium oxide is its refractive index is 1.8, around 1.8 to 1.9. On the other hand, the refractive index of the zirconium fluoride fiber that we use in our laser system is 1.48. So it creates like 8 to 10% back reflection. This is not good for most of the lasers. So another fiber we tried is the silica fiber. First of all, splicing a silica fiber to a zirconium fluoride fiber is like one of the most challenging process that we had because of the transition temperature difference. One is around 1000, the other one is around 200 Celsius. So, but still we did it. And then as you can see, it survived. It survived up to 100 Celsius, but the temperature in the beginning was already 75 Celsius. If you make a quick calculation, if you use a 100 watt system, probably the temperature will reach around 300 Celsius. This is not good for the future. And another good advantage for using silica fiber is they have low refractive index. It's matching with the zirconium fluoride fibers refractive index. But as I said, it's very challenging to fabricate this kind of end caps. So the last thing we tried the sapphire fiber. Here you see the sapphire fiber had like pretty much the same behavior as the silica fiber. But again, at the beginning, the temperature is like a little bit high. And also there's a trend which increases when the time passes. And because of that reason, maybe they are not very ideal for many systems because it's very challenging to fabricate as silica fibers. And it's also not possible to just determine the length of this fiber because it's crystalline structure. You cannot cleave this fiber, cut this fiber. You have to polish. And it's like very challenging glass. Because of that reason, maybe it can be used for like multi-mode beam outputs for some kind of medical applications at low power. So here you see the graph that pretty much a couple of all the oxide-based fibers survive for 100 hours, but we don't know the answer for more than 100 hours. We know right now maybe like a couple of thousand hours they are ideal for the germanium oxide. But really, what we will see if our power levels goes like 50 to 100 watt, we have no answer. By considering this kind of questions, we just wanted to coat the fiber faces with silicon nitride. So what we did is we just built the fiber end caps like what I show you, and then we put silicon nitride on the face of these fibers. This silicon nitride is like pretty well known in the electronic industry. People are using it to cover their electronic materials to protect their electronic components from the humidity. So we did the same thing actually. We just coat the fiber with 25 nanometer thickness of silicon nitride, and we operated the system at 20 watt, and we try to understand what is the mechanism behind that. So as you can see here, you will see if you have an end cap with fluoride fiber, it was failing. This is the graph that I showed you before. But if the same fiber is coated with silicon nitride, we show like there's no sign of like increasing temperature, and it allows us to operate the system at long term without any problem. In the second graph, you will see the aluminum fluoride. It's also like the same behavior. Aluminum fluoride is like failing in the beginning. If there's no coating, with the coating, it has only 40 Celsius and the temperature is not increasing. And in the third graph, you see the sapphire fiber. It has pretty much the same behavior. So actually we solved this problem. And then now this coating should be like well optimized in the future to be used in the like 100 watts of systems in the future operating at 3 micron. And also for the high pulse energy systems, this kind of coating could be like very ideal. So as a result, in last couple of years, we showed different kind of demonstrations for 3 micron lasers. And with these demonstrations, we have achieved the record efficiency, output power, and pulse energy, and also the peak power. And we also kind of solved this OH degradation problem of the 3 micron fiber lasers by coating them with the silicon nitride coating. And we know that still there is a room to improve each of the parameters of this kind of lasers. And I guess the future for fluoride fiber lasers operating 3 micron is pretty bright. And there might be like new applications already, like people are discussing semiconductor processing by using this kind of lasers. So probably there will be many other applications will come in near future. and this laser will help to people to just use them in their applications. So before I finish, I would like to acknowledge a couple of people. First of all, Dwayne Miller. He's the pioneer of this 2.8 micron optical parametric generators, and I've worked with. And Martin Bernier and Real Valley from Laval University. They are the pioneer of 3 micron fiber lasers and mid-infrared fiber lasers. And also a special thanks to Darren Kramer, who allowed me to use the videos that I show you. And also he's the one of the pioneer of this solid state laser operating at 3 micron and investing a lot to just improve the performance of such lasers. Thank you.
So thank you very much for this very inspiring talk with a lot of applications. So I think, sorry, small technical issues here. Let me share it. So we would also like to share with you a token of appreciation for giving of this talk here and there at IZTECH. And so this is our certificate that we'd like to hand to you, and as well we also made a donation in your name to our students to support young people in science. So thank you very much for both.
Thank you so much for that. I appreciate it.
So, and I would like to ask the audience whether there are any more questions to Yiğit. So, there is a question.
Hello. What kind of laser types are you using in surgery, small mode or single mode?
It's a very good question. In general, it doesn't matter either it's single mode or multi-mode, but since in this kind of applications, the fibers we are using are sapphire fibers. Sapphire fibers are not, it's not possible to manufacture sapphire fibers with like very little core size. They are either 100 micron or 200 micron core size. Because of that reason, whatever laser you use in medical application, it turns to be multi-mode because you just insert these sapphire fibers and it turns to multi-mode. But theoretically, there's not that much of a difference between using multi-mode and or single mode, because what's going on with this laser is just you just ablate the material. So the tissue won't understand it's a single mode or not. The basic advantage of using single mode laser, if you are focusing this, since we are not focusing, we are going with the fiber to the tissue. In general, for us, multi-mode lasers are better because the transmission of also multi-mode beam from a laser to the application area is much easier compared to single mode laser.
Thank you so much.
Thanks again, Yiğit.
I thank you.
That she has won multiple awards. So the Early Researcher Award in 2016. That same year, she also won the Petro-Canada Young Innovators Award. And she has also a fellowship, a leadership in teaching and learning fellowship during 2017-2019. Now, beyond that, she's also in multiple editorial boards, and she is editor and associate editor of various journals. Well, let me not go into the details. I think her talk will speak for itself. So please, Ayşe, I welcome you to here in IZTECH, well, online. Please go ahead.
All right. Thank you very much for the invitation. Maalesef yanınızda olamadım. Ama umarım en yakın zamanda buluşacağız biz bir yerde. İnşallah İzmir'de, inşallah Kanada'da. Kanada'ya da davet ediyorum hepinizi. Today I'm going to talk about our work over the last many number of years, but specifically looking at how we can harness diblock copolymer templating for tailored, in particular, perovskite nanoparticles for a variety of photonics sort of applications. So thank you very much for this invitation and this opportunity to talk about our work. I really appreciate it. I wanted to first highlight, of course, that even though I'm the one who always does the talking, this is the work of many years of many students at 2 universities, actually. And so I wanted to highlight them up front. They've been working very hard for many years to get us to where we are now. And I actually moved my research group from McMaster University, where I had spent the first 10 years of my career, last year to Concordia University, where I joined the Center for Nanoscience Research. And here is a picture of our beautiful new building, the Applied Sciences Hub, where my labs are. And we focus on nanoparticle synthesis and deposition. We do a bunch of advanced spectroscopies, and also we integrate our nanoparticles into various types of optoelectronic devices, solar cells, LEDs, lasers, etc., all within our lab. So I welcome you to come and visit us in Montreal and come and see what we're working on. We'd love to host you at any moment. Please don't hesitate to reach out to me. You can see here that those are my my email addresses. We're always also looking for new students. So anybody interested in doing a advanced degree, a PhD, or even a postdoc, please don't hesitate to reach out to me. We're always looking for excited young people. So really the essence of our work is we like to use the motto that we drive engineering with nanoscience. And it's about tailoring various surfaces, interfaces, and heterojunctions with nanostructures at various levels to make disruptive technologies. So we focus on different types of materials innovation, understanding synthesis, understanding formation, understanding assembly, and probing those materials with various photophysical sort of ways, with the ultimate goal of integrating devices. And we work from 1D structures all the way into full devices to understand at every point sort of the essence of what's happening within these systems. So functional nanoparticles for photonics covers a wide variety of applications, and various types of nanomaterials have enabled on-chip isolators, for example, or lasers, taking advantage of the shape of nanostructures for interesting plasmonic behaviors, making a wide variety of photonic sort of objects and devices. But one of the key problems with upscaling to industrial use, though a lot of these things have been shown in the lab, getting it to industrial use has been quite challenging because the scalability of these systems, of all nanoparticle systems, is limited by heterogeneity. So the ability of making high performance, it really helps to have uniform monodispersed nanoparticles in organized arrays. And the ideal way of doing this is something like this, right? So we have nanoparticles that are all equal in size, equal in spacing, and form a nice organized array. And I always like to show this sort of propaganda schematic view because right beside it, the way that we achieve this sort of approach, or we go about trying to do this, is through a diblock copolymer templating approach using solution methods, right? So the idea of making our nanoparticles in solution so we can produce them on various surfaces. And this is really as I said, the propaganda view. And this is an actual AFM image of nanoparticles that are produced within our lab, right? So we're able to actually achieve this level of monodispersity and organization as our sort of propaganda schematic shows. Now I'm going to go into a bit more detail about this process, and kind of the first bit of my talk is really about the reverse micelle templating itself, and then we're going to talk a little bit about perovskites and their interesting uses. And the basic process that we use involves making what we call micelle nanoreactors. So a micelle are we start, in order to make these micelles, we start with what are called amphiphilic unimers. And basically, an amphiphilic unimer is a material that has a hydrophobic and a hydrophilic end. In our case, we use polystyrene 2-vinyl pyridine. And the interesting thing about these sorts of materials, because they have a hydrophilic and a hydrophobic end, above a critical concentration called the critical micelle concentration, these sort of unimers that are floating around, these are polymer type chains that are floating around in a solution, will spontaneously form what we refer to as micelles, which is a macromolecule collection of these single unimers, shown kind of schematically over here in the corner. And if you put them in a polar solvent, well, what ends up happening is that the hydrophilic ends will be on the outside. And these are, for historical reasons, referred to as spherical or regular micelles, because people were first making micelle type structures in water and various types of polar medium. And in fact, everyone has encountered this kind of micelle because this is what soap is, right? So soap is basically this sort of structure in water where one end is interested in the water and one end is affiliated with the soap, with the dirt. And so it allows, basically by surrounding the dirt or surrounding whatever fatty molecule on the inside and having these polar ends on the outside, pulls it off of your dishes, for example, into the solution. Now, if you put the same kind of structure, this amphiphilic, hydrophilic, hydrophobic structure into a nonpolar solvent, something like an organic solvent, they tend to form what we call reverse micelles, where the hydrophilic portions or the water-loving portions are on the inside and the outside is this sort of hydrophobic shell. And the beautiful thing about this is that you can take advantage, therefore, of the little pocket of polar solvent or polar region inside to start to do some interesting chemistry. And so that's basically what we do. So what we do is we take these, these little nanoreactors that are on the nanoscale, made up of these polymer materials that have aggregated into these structures, and then we add various types of reagents to them. So we add different salts, we might add different reducing agents. You can do anything that you could do in a beaker, you can start to do inside these tiny little nanoreactors, nanobeakers that we often call them. And there's 3 principal types of reactions. So I won't go too much into the chemistry, but basically it's amenable to a variety of different reactions, basically things that you can do in solution, in the aqueous solution, you can do inside of these micelles. And there are a wide variety of methods to do it. So we've developed in our labs different approaches for making nanoparticles that include a one-step loading. So you add a single precursor and it forms nanoparticles through post-processing. We have 2-step loading where you add 2 different reagents that react with each other in order to form various types of interesting structures. And you can even expand that beyond to 3 and 4 and 5-step loading to start making interesting complex nanostructures, Janus particles, core shell structures, etc. So there's a wide variety of materials that are available to us when we start to use these kinds of templates. And our templates have been very very giving, actually. And within my lab, we focus on 3 major areas where we target nanoparticle applications in energy, in sensing, and in magneto-optics. And over the years, we've produced a wide variety of functional nanoparticles for various, both to understand the science of formation, the science of the interface modification, but also to introduce into devices. And these include things like metal oxides. This is really where we started. Metal oxides are very important for optoelectronics, and we've produced a wide variety of very uniform nanoparticles that form different kinds of arrays. And again, at the corner here, there's a number of our publications. If anybody's interested, please, please do look them up about different recipes for these metal nanoparticles and their uses. We've also produced, of course, we've introduced them into optoelectronic devices. We've also used them for water splitting. We've also produced a wide variety of dielectric halides. Again, interesting materials for integration into organic electronics, so tuning the surface work function, for example, and then ultimately modifying both OLEDs and OPDs, organic photovoltaics and organic light emitting diodes, using these dielectric halide interlayers. We've also produced a variety of metals. This actually is the most common usage for reverse micelle templating, and we've also started going into them, making different kind of precious metals, but small amounts that cover the surface. And interestingly, with these small amounts, you can actually mimic a fully covered surface properties. And this is something that we've been very interested in recently, looking at, for example, absorption of proteins onto different surfaces modified by these nanoparticles. We're also moving the nanoparticles into and out of various types of arrays, various types of substrates in order to expand the usage of these nanoparticles. We're also able to make some nanoparticle graphene composites to take advantage of these composite type structures by printing them using graphene, for example, onto different polymer surfaces. We have produced a wide variety of perovskites, and I'm going to go into a great amount of detail them in a little while. And with these perovskites, we've been able to achieve very interesting behaviors that I'll mention, that I'll delve into a little bit later. And then finally, we've produced a number of what we call core shell type structures. So using more sophisticated synthesis techniques, you can start to build up different layers on the surface to get different functionalities. And we've both been probing them sort of fundamentally and then also implementing them in various devices. Now, synthesis control is critical to successful nanoparticles because the nanoparticles themselves, there are so many different knobs that we can turn. There's a lot of moving pieces to try to get an actually successful nanoparticle that you can use for a particular application. And so an example from our research, we've seen, for example, if you're making perovskites and you change the order of the precursors, you need to use 2 precursors to make a lot of perovskite materials. If you start with the organic component of this perovskite, you get beautiful arrays of nanoparticles. But if you start with the halide component, so lead iodide, for example, you end up with dissociation of the micelles and destruction. So you need to be very careful in tuning your recipes to achieve the kind of behavior that you want. That's also true if you're going into more complex structures, like making these core shell particles, whereby just by changing the amount of the third precursor, for example, in this case, gold, we're making gold tins type structures. The more gold that you add to the surface, you start to lose some of the beautiful organization, but you start to introduce new functionalities, new oxidation states that didn't exist, either in gold nanoparticles by themselves, that starts to affect how we can use them in various devices. And a good example of that is, in fact, this idea of making core shell magnetic nanoparticles, which we used for optical isolators in photonic circuits. And the basic process is very similar to what I mentioned. We start with these micelle arrays. You can see we have a very nice 2-dimensional array of similarly sized micelles made up of our base structure. We add a very basic tin salt. And when you add tin salts in various compositions, you get, again, a good registry between the micelles themselves and the nanoparticles. The nanoparticles tend to be slightly larger because they've infiltrated inside these micelles. And we can probe them. What we see very interestingly is that when you produce them just as is, there tends to be a lot of, this is Raman spectroscopy, which gives us insight into some of the bonding configurations. And what we see when we initially produce these nanoparticles is that they don't have a fully crystalline structure, even though they look very, very ordered. They have a lot of oxygen defects, which we see with this Raman spectrum in the middle in green here. This peak in the middle indicates the prevalence of oxygen defects using our approach, which gives it a magnetic behavior from tin oxide, which you don't normally see. Now, we can also take this one step further by adding a second precursor. So in this case, this is a gold salt to make kind of a core shell type structure, where we have our micelle array on the outside. We have our micelles on the outside, and on the inside, we have both tin and gold. And interestingly, the Raman spectrum of these tin gold materials without annealing resemble much more the sort of crystallinity that we see when we, after etching and annealing our nanoparticles in order to sort of boost their crystallinity. And we can use grazing incidence wide angle scattering to look into the structure and understand what's actually going on. And if we have a thin array of materials and do a full plasma etching to remove the polymer completely, what we see is that in all cases, whether we have tin chloride by itself, if we use a precursor like ethanol to try to encourage the oxidation of tin chloride to tin oxide, or if we use this tin chloride with gold combination, we see the formation of sort of different polymorphs of tin, including tin oxide. But in the case of our gold, we start to see some other new structures, which are also heavily oxidized, or oxygen vacancy rich tin oxide materials. And if we do an incomplete plasma, so we don't try to burn off everything, we want to sort of capture what's happening in the middle, we can see the formation of that the tin itself requires the plasma in order to finally convert tin chloride into the tin oxides, though they tend to exist simultaneously if you stop the process in between. But the tin gold combinations are an internal reaction of oxidation reduction, simultaneous oxidation reduction of the two components. So you actually get both tin and gold forming inside without needing to do any plasma etching or doing complete plasma etching if you have enough gold. So the ratio of gold to tin becomes critical in fulfilling that reaction, for example. So once we discovered that we can produce these sorts of interesting structures, we also wanted to quantify the shell thickness, and using simulation of electron spectra for surface analysis, using these sort of new modern tools to estimate and simulate the types of structures that could be possible, combined with some machine learning, we were able to observe that the gold is forming predominantly on the outside of the tin. So the tin oxides are forming inside and the gold is forming on the outside. And you have a very, very, very thin layer of gold, only on the order of of 1 to 2, roughly 5 nanometer thickness, that mimics basically a full gold system. So by making these structures, you can actually get the properties that you'd expect from a fully gold structure, but also you start to harness some new functionalities that weren't possible by just having tin or gold by themselves. And one of those is that we have a boosted absorption in the visible by a coupling between the plasmonic effects of the gold and the magnetic properties of the internal particle. And this has been observed in sort of gold-shelled iron oxide, and we were the first people to show it also occurring simultaneously in tin oxide nanostructures. So we were able to get magnetic particles from tin, which is not normally a magnetic material, and then enhance that effect by shelling it with gold and being able to having a tunable magnetic response. This allows us to incorporate it into things like waveguides to use as an optical isolator, basically a light valve for an on-chip type device. So understanding the synthesis methods are very important to be able to actually achieve new properties that you couldn't get from other systems alone. Now, the rest of our process basically involves taking these particles that we've made in solution and then coating them on various surfaces. And in my schematic, I'm showing here that we're using spin coating, but actually our particular approach is amenable to all types of printing techniques: dip coating, spin coating, slot die coating, even different types of electrospray with the same sort of structures. So we get similar regularity of nanoparticles. We get similar sizes. We also get similar kind of coating on the surface, which you can tune using the different parameters to achieve arrays of various sizes. The nice thing is that one of my students quite recently published a very nice invited paper where we show that we have complete control over the interparticle spacing between the particles as a function of various deposition parameters, such as spin speed, for example, or dip speed, or slot die coating speed, and that we can achieve similar amounts of disorder driven purely by the the intermolecular order, so the self-assembling of these nanoparticles on the surface, regardless of which technique you use, you can start to see the similar types of structures being formed. The nice thing about our reverse micelle templating approach, not only can we deposit it from basically any any type of method that is amenable to a solution, but you can also deposit it on almost every surface, right? So you can achieve similar size, similar structures, similar spacing between particles, regardless of the surface energy of your substrate, for example, and regardless of, you can tune all these different parameters, and we've even developed ways of putting it onto certain substrates that may not be amenable to to direct production. So you can produce it directly, or you can transfer the particles onto other surfaces for different applications that may require those things. And the final step of making our particles often involves removing the polymer by using a plasma. So I mentioned using oxygen plasma earlier to draw some of the reactions. The plasma has the sort of twofold effect depending on how you produce the material. Either it just removes the polymer and leaves behind nanoparticles, or it can actually be involved in the synthesis process, as we saw with tin oxide, for example. And we get nice registry between the nanoparticles that are produced after plasma etching and the reverse micelles that are loaded with the precursors before plasma etching, because plasma etching is a low temperature, non-invasive type of approach to removing the polymer. So we don't heat them up. We don't have to apply different kinds of solvents to remove them. All we do is apply a plasma, and you get direct registry of nanoparticles where micelles were, which is a very nice approach. Now, you can imagine that the design space to make nanoparticles and make nanoparticle arrays is vast, and there's many different things that you can change, different recipes you can make to produce different sizes, different shapes, different things. So a lot of our work in the last number of years, 5 or 6 years, has really focused on trying to understand the design rules to once you turn some of these knobs, such as the mixing time or the amount of precursor versus the polymer, or even the polymer itself, to understand what is being predicted in the outcome. Now, because we get all sorts of different structures, we need some tools for quantifying those structures. And one of my students developed a couple of years ago a Mathematica package that you can use to understand the organization of nanoparticles on a surface, which is called Dislocate. And you can go to our GitHub if anybody's interested in using it. The idea basically is that from any kind of image, either an optical image, an AFM image, an SEM image, you can extract immediately all of the spatial statistics, so the distance between particles, their Voronoi sort of structures, the pair distribution function, so how organized they are. Obviously, the more organized they are, the sharper these peaks get, for example. And so you can immediately just from a picture like this, upload it into the Mathematica file and get all of this spatial statistic information sort of at your fingertips at a glance. So if anybody's interested in that kind of information, please don't hesitate to reach out to us or go to our we use that particular tool as one of the things that we're interested in is about uncoupling the geometry from the material properties. So trying to understand when you have nanoparticles arrayed on a surface, how much of the influence of those particles comes from the geometry of their organization, because in many applications, organization of materials has shown to greatly affect the surface properties, versus how much of it comes from the internal material itself. So is it the array that's causing the sort of properties that we're interested in at the surface, at the interface, or is it the material itself, or is it a coupling of those two? And how important is it in different applications is something that we've always been striving to understand. And sort of 3 examples from our recent work that highlight some of these things is looking at dispersion control to tune the charge injection in organic semiconductor devices by having very, very small amounts of these nanoparticle arrays at the surface, where the coverage for different materials becomes critically important. We've also shown that if you have an ordered array versus a disordered array, you see enhanced water splitting at iron oxide nanoparticles. And we've also seen the impact of having different size nanoparticles for example, protein absorption on different surfaces. So again, the idea is to uncouple what is a material property versus what comes from the geometry by making lots of different materials with similar geometries, for example. So really, this is my propaganda pitch about what we do in general. We really produce nanoparticles from solution using this micelle templating approach. And the micelle templating approach gives us access to a wide variety of both interesting physics as well as interesting applications. So this is really the sort of bringing together of science and engineering to use, as I said, driving engineering with nanoscience. So now I want to switch gears a little bit and talk specifically about our recent work in perovskite nanoparticles. And perovskites have emerged as these organometal halide perovskites have emerged really as a fundamentally new material that is revolutionizing a wide variety of applications. Particularly, you may have heard about perovskite solar cells, but actually there's a wide array of applications where perovskites are starting to emerge as really bringing new interesting material science, new interesting physics into play, getting us to new types of applications that we hadn't been able to access previously. And so today I want to focus particularly on some of the work we've done looking at some optical isolator type materials, these core shell type structures that I already mentioned, these tin gold examples, as well as other sort of interesting optical phenomena. And we're going to predominantly talk about different perovskite structures and some of these core shell systems. So just as a brief sort of primer on organohalide perovskites, basically a perovskite is a particular type of crystal structure that's defined by these sort of octahedral shapes and a caged molecule or caged atom within that's able to that sort of freely move rattling around within a cage of our halides. So we typically have our organic material as the as the rattling around molecule or rattling around atom, and the cage structure is usually made up of the halide portion. Right? So this particular configuration is what we refer to as perovskites. They were discovered almost more than 100 years ago, actually, and were well described and well understood in oxide materials, but the real revelation happened in producing it with halides and then using them in solar cells, approximately 10-15 years ago. And the really exciting thing about these sorts of structures is that they have this ability to be tuned and this flexibility in the crystal structure, which allows for accommodation of a wide variety of different ions and a wide variety of different defect structures while still maintaining their properties. And so it's very possible using the same combination or very similar combinations of precursors to span the visible spectrum all the way from ultraviolet into the infrared, basically using achieving these same structures, so that there's a tunable band gap that's related to how we manipulate the crystal structure. And this example here are actually particles all that we've made in our lab and their emission properties. And so you can see that using the same template, some very similar precursors, we were able to make nanoparticles that emit across the visible spectrum. And of course, the real sort of excitement, or one of the major excitements about these perovskite materials, has been in the solar realm. And you can see that if we zoom in here, the latest generation of perovskite cells here are already challenging silicon. So within the span of about 10 years, they went from being an interesting novel material to being able to replace commercial silicon. There are a number of companies that are starting to roll out production scale perovskite solar cells hopefully in the near future. It's always in the near future, but this is sort of the general idea. So this has been one of the major interests. And of course, one of the reasons that it's exciting is, unlike silicon, which is brittle and heavy, you can actually start to make all sorts of new form factors because you can produce them, for example, from solution, and they can be ultralight and ultra thin compared to our traditional crystalline silicon or polysilicon type structures. Now, why might we want to have nanoparticles? Then there's a few reasons to pursue nanostructures for solar cells, but also for other types of photonic applications. And fundamentally, what we see is that perovskite nanoparticles exhibit enhanced carrier lifetimes compared to, say, a thin film. So within microcrystals or nanocrystals, you start to see not only a shift in the energy, so the band gap can be tuned by making nanocrystals, but they also have longer lifetimes. And because of the longer lifetime, you start to see interesting applications in lasing and light emitting diodes, for example, using these nanostructures and their collective sort of behavior. Having nanoparticles also allows greater control of modifications in structures. When you try to make a big thin film, you have there are a lot of limitations in trying to make pristine thin films. In this case, we're far, far away from pristine bulk films. And so we have a lot more ability to play with these behaviors and get interesting structures and interesting behaviors. So this is a good option for high performance optoelectronics, but again, the scalability is limited by how homogeneous those nanoparticles are. And so one of the beauties of using the micelle templated approach compared to other synthesis approaches, so here I show an example of a traditional ligand-assisted approach, which tends to form not sort of zero-dimensional nanoparticles, but these sort of nanorods or platelet-type structures where you have one preferential growth direction. And using our templated approach, we can actually form beautiful arrays of nanoparticles that are all self-similar in size and have uniformity that's really quite high. And what we found very exciting is that this micelle templating approach is basically a universal approach to organohalide perovskites. We can modify the both the A site cations, so the organic portion of it. You can modify the halides. You can also modify even so lead is the common lead halides are the common, most easily formed halides, but there's been a big push to remove lead, and you can move into things like tin, and even using tin, we've been able to produce these sorts of perovskite materials. And as I mentioned, we've also branched out into making these core shell type structures, all within the same micelle template, just by changing the different precursors. But of course, you have to get the synthesis right. So as I mentioned off the top, if you even if something as simple as changing the order of adding the different precursors, which in the case of bulk perovskites doesn't make a huge difference, in this case, it leads to either the formation of beautiful nanoparticles or nothing, right? Or in fact, if you pick different structures, you might get multi-particle formation. But one beauty of having all this control over the synthesis, and that's really one of the benefits of using reverse micelle templating. You can see this here is a photoluminescence intensity spectrum showing the speed at which the perovskites form within the micelle structure, and the numbers here tell you that in our case, it takes us quite a long time, up to 20 minutes or even 24 hours before we have a fully formed perovskite. And this is in contrast to regular perovskites. When you usually mix two precursors together, they will form spontaneously under a minute, which is great, but also leads to these uncontrolled growths in various directions and less control. So we have, with this reverse micelle templating approach, a way of tuning or slowing down the reaction kinetics so that we can achieve interesting structures that can boost the photoluminescence quantum yield, for example. And one of the things that we've discovered in that, of course, is that if you change the amount of precursor, you can see a huge boost in the performance. For example, instead of having a stoichiometric relationship between the two precursors, which is what is commonly used in bulk synthesis, if you reduce the amount of lead iodide, you don't get some of these lead iodide crystals precipitating out of solution, and you get a heavily influenced or heavily increased amount of emission, boosting our photoluminescence quantum yields from around 20% to over 60 or 70%, almost 80%, just by changing the ratio of the precursors into substoichiometric relationship. And you do this without actually changing really the nanoparticle size or their distribution. There is a slight change in the size of the nanoparticles, and you do see a slightly more particles being formed, which tells us that we're not using some of those micelles for making some of these lead iodides rather than the perovskites. And you can see that the improvement, we almost doubled the performance, the photoluminescence quantum yield for this particular structure. And for other types of structures, we can see similar sorts of approaches by just changing the type of perovskite that we're making, by changing from methylammonium lead iodide to pyridinium iodide, for example. You can eliminate all of the lead iodide precursor and actually get high performance directly from the crystal. So understanding some of these different nuances allows us to get high performance, high yield type materials. There you go. And again, because we have lots of different knobs to turn, we can start to play around with not just the precursors and their ratios, but also the amount of polymer. So by boosting the amount of polymer that we have, just from 3 milligrams concentration to 20 milligrams, we can increase the emission efficiency almost fivefold by changing the polymer molecular weight to have larger or smaller diameters inside the core, because again, the micelle is what's driving the nanoparticle size. For example, we can improve our performance. You can see here, this is actually a cut image. So these are all photoluminescence images. We have very, very little luminance from our high molecular weight polymers, but as we decrease the molecular weight and make the particles slightly smaller, we start to see a huge boost, this is 10,000 times improvement in the emission properties from the same source of structures. So using some of these learnings, we're able to achieve low polydispersity with high emission efficiency using this sort of correct recipes, right? So again, as I mentioned, this is a universal approach. So we can change the A side cation, we can change the B side cation, we can change the halide, we can interchange all of these different materials to make a wide variety of emitters across the visible spectrum. Now, in addition to just being able to produce emission at different wavelengths, micelle templating seems to give rise to structure and properties that are not readily observed in other systems. So, for example, one of my students showed a couple of years ago that if you take methylammonium iodide and load it into these micelles, you can produce beautiful arrays of single particles that have different emission properties just by changing the halide. So you start with the same first precursor, and you change the second precursor, and you get a wide variety of different materials or different emissions. And this is not possible. So some of these combinations, if you just produce them in solution, if you just mix them together, they wouldn't spontaneously form an emitting particle. And even if you use some of the traditional synthesis methods, you still can't produce these sorts of emitting particles by using these precursors. So it gives you access to a whole new set of precursors that you wouldn't necessarily be able to use just in the bulk. Additionally, what we've seen is that by producing these things inside the template, you see a shift in the band gap that is happening in the opposite direction that you would expect from the particular substitutions that people know, right? So usually if you add bromine to these sorts of structures, it tends to push them into the green. But in using the micelle templates, instead we start to see the formation of things that are emitting in the red. So you see a red shift by through what we think is a process of confinement. So this allows us to tune the emission profile with the same micelle templates. But beyond that, we can even tune the emission profile using the same precursors just by changing stoichiometry. So as I showed in one case, changing the stoichiometry boosts the photoluminescence quantum yield. But for different precursors, again, ones that you couldn't necessarily use if in the bulk, you can start to get a mixture of emission properties where you might even have two stable emitting peaks using and at the same time. And this is very different than what happens in, with when you're not using a micelle template. So for example, if you were to mix together cesium lead bromide and cesium lead iodide, after 2 minutes, you would see an intermediate phase forming immediately rather than having stable two-phase emission, for example. The beauty of two-phase emission is that it starts to allow, what we've observed is the development of large Stokes shifts in these materials. So we have absorption occurring in at one wavelength, but the emission happening well outside of that absorption envelope. So you start to see large Stokes shifts that we can take advantage of just by tuning the properties. And in fact, for one particular system, this is the largest Stokes shift that's been reported so far within perovskite materials. Perovskites typically are not prone to showing large Stokes shifts because they have a tendency to self-absorb because the absorption envelope is usually quite close to the emission profile. But we were able to take advantage of reverse micelle templating to actually produce these large Stokes shift materials. These large Stokes shift materials we then utilized in organic photovoltaic devices as sort of a down conversion layer. So we were able to down convert ultraviolet light into usable light, which when you matched the emission profile of the nanoparticles with the absorption profile of your organic molecule, you see an enhanced behavior. So an increase in the short circuit current, an increase in the open circuit voltage in the case where the emission and absorption profiles were matched together. So in that case, we have green with P3HT PCBM and red with PGB7 PCBM, where the emission is tuned very well to the absorption region of those molecules. And we know that it's happening from down conversion because if we change our light source so that we eliminate any of the UV components, we see no similar improvement. Right? So we're definitely seeing a down converting layer to take advantage of UV light into visible. In addition, micelles actually stabilize different kinds of metastable phases that aren't, again, accessible in the bulk. So for example, for methylammonium lead iodide, we're able to form a particular phase that's only observed usually under low temperatures, which is why we're able to get sort of self-similar nanoparticles rather than these growing platelets. We also see the formation at room temperature of formidinium and lead iodide, which is usually unstable at room temperature and tends to spontaneously transform from the useful emitting delta phase to the alpha phase immediately, from the alpha phase to the delta phase immediately at room temperature because its transition temperature is around 50 or so degrees or 40 degrees. And so by using the micelle as a stabilizer, we're able to form at room temperature these sorts of inaccessible structures. And where we have the confined environment of the micelle providing strain onto the system to allow those things to form at room temperature. And that's really what we've discovered over the years is that the micelles seem to exert pressure on the growing crystal, which allows it not only to produce, for example, formidinium, but we can take a material that was not actually active, optically active when you're producing it in the bulk phase, and by introducing it into the micelles, we actually made it optically active within the visible region so that you could observe it. And this allowed us to push the emission profiles somewhere into the infrared, for example. And we see the evidence of strain playing a role when we have micelles versus when we don't have micelles. And finally, the ligands themselves, having these polymers on the outside, really enhances the stability of these particles. So one of the real drawbacks to perovskites is their instability when exposed to air or exposed to water. And when we have our nanoparticles protected by these polymers, then it can stay with very little change. So this is about a 10 or 20% drop in the emission intensity over almost half a year. And if we introduce them into water, there's a slight shift. This is after dunking it into water for 1 hour. We see a slight shift and a slight loss, but again, very limited compared to what you'd expect for these materials. And if we play around with the chemistry and have some more stable cations, which, as I mentioned, these were cations that were not possible to form perovskite structures without the micelles. Once we introduce these more stable materials, then we see almost, this is 410 days, so more than a year, these particular materials show almost no loss, so less than 5% loss of emission properties over a long time. So this starts to bring them closer and closer to commercialization. However, one drawback of having these polymers on the outside, our polymer, you may remember way back at the beginning, I mentioned that the outside of our micelle structure is made of polystyrene. Polystyrene is not a conductive polymer material, and so it makes it the reason that we only put it on as a down converting layer in those other OPVs is because we need to have the polymer there, and so we can't incorporate it directly into a device. So one of my students in the last couple of years has actually developed a really interesting approach using 3-step loading to make capped perovskite nanoparticles, where we surround the perovskite with a metal oxide, for example. And I'm going to show a particular example of titanium here, where we're able to make highly stable titanium shelled FAPRI, or this formidinium lead bromide perovskites. And you can see here's an example, a TEM image of the perovskite in the center and our titanium shell on the outside, forming a nice thick shell. And as you add more and more precursor, the titanium chloride, you can see that you get a thicker and thicker sort of shell. And what that means is that here is our emitting sort of material, our perovskite material emitting at high intensity with the shelling. And if we, for example, plasma etch it, so to try to remove that polymer, the polymer shell from the outside for 10 minutes, we see only a small loss, maybe 20% loss of the emission properties while removing the polymer. If we were to try to do that with FAPRI by itself, we would have almost no emission properties at all, right? Because oxygen plasma is bad for these sorts of structures. And so by introducing this thick titanium shell, we're able to protect the nanoparticles from the perovskites from being destroyed. And this allows us to also do interesting things like annealing it for at very, very high temperatures for perovskites for a long time. So 300 degrees Celsius for 3 hours, again, would usually destroy FAPRI. But we were able to still see some emission. I mean, there's a huge loss. It's not perfect, but we still see some emission from those structures, even though they've been exposed to these high temperatures that should lead to a phase transformation, for example, of the FAPRI into the non-emitting phase. So we're able to form these really highly stable particles, and that allowed us to actually introduce them inside the device instead of on top of the device. And what we see is that an improvement, because we have this coupling between the titanium and the perovskite, that is better than titanium by itself, and much better than the perovskites by themselves, because the perovskites by themselves have been destroyed by being turned into lead, for example, lead iodide, lead bromide. So we're able to tune the efficiency and put them inside a device. And this is a stepping stone for actually making full perovskite devices in our lab. And as an aside, it also, interestingly, rather than having sort of a green emission, as we did from the original perovskite, shelling it with these titanium particles has titanium oxide has turned our very, very green emitting particles into ones that emit white light, actually. And we're able to get that because we have the ability to introduce all three types of halides through our multi-step process. So we have both iodine, which tends to emit in the red, we have bromine, which tends to emit in the green, and we have chlorine, which tends to emit in the blue. And all three of those are stabilized because of the presence of the micelle, allowing the formation of those structures. And so we get this broad white emission that's well enhanced compared to what titanium would normally emit at, for example. And in addition, we also see with something else, with nickel, for example, we can actually enhance the emission. So there are certain polymer materials that don't emit very strongly, but without changing the size of the particles too much, we can see almost a 10-fold increase in the emission properties just by adding small amounts of these chlorides, for example. And it also leads to interesting sort of transient behavior that we're still in the process of understanding what's happening in these systems, where we see simultaneously dual emission under various excitation wavelengths. So really, in a nutshell, synthesis tuning, as we were able to do because of the beauty of our reverse micelle templates, allows the formation of lots of different perovskites, which we can use for different applications. So I showed an example of how we got large Stokes shifts that were not possible in the bulk, that allowed us to then use them as these down converters, for example. We can make transparent films that cover the visible spectrum into the ultraviolet and the infrared, pushing into some of the telco type things. So we're a little further away from mid-infrared at the moment. And then because we're able to change the precursors pretty much at will and tune the different interactions, we can start to see the development of these new interesting features of from these core shell type structures, interesting transient luminescence, enhanced photoemission, enhanced yields, etc., from small amounts of doping. And so, really, that's all I wanted to talk about today. We also work on other things. We've spent a lot of time looking at OPVs, and you're welcome to come and see some of our work on looking at nanoparticles and OPVs of different kinds beyond perovskites, as well as battery type materials we've recently been delving into. And really, as I said, the whole essence of our work is to try to drive engineering and applications harnessing the beauty of nanoscience. And really, nanoscience right now has the capabilities of introducing a whole new paradigm of applications that were not possible in bulk systems. And we're hoping to contribute to that a little bit. So with that, I'd like to thank all of our collaborators around the world. We've been very blessed to work with many, many exciting people who brought a lot of amazing things to our work. And I want to thank the funding agencies, of course, for supporting different aspects of things that we've worked on. And I'd like to thank you, and I'd open the floor for any questions.
So are there any questions from the audience? If not, I actually have two questions, but I'm only going to ask one then. So I was thinking, so you have these micelle structures. Mm-hmm. It should be possible to make them kind of like more elliptic or elongated. Did you try to make kind of ellipsoids, nanoparticles, or some different geometries?
Yes, so it is definitely possible using micelles with different kinds of micelles with different structures to make triangular shapes, for example, or ellipsoids, or even square structures. Those things are all possible by tuning the polymer a little bit. And we have started to go in that direction because we're very much interested in these plasmonic structures, and the triangles are the big thing for plasmonics, obviously. But the design space is already so vast just to make, spherical particles that could be that. I think that's going to be the focus of our next set of work, maybe, but definitely an interesting area. This is one of the beauties of this templating approach, because you're using a diblock copolymer. It applies to a wide variety of materials that have different functionalities at the various ends, at the two blocks. But you can imagine that as soon as you start to go into that realm, it gets even more complicated, right? So now you have a third dimension that you have to take care of. So it's definitely possible, and we have done some of it, but it's still a work in progress.
Thanks a lot. Then I would like to thank you. I have to switch. Yes, this is the correct one. Sorry, quickly. All right, great. So we would like to give you a token of our appreciation. So with this certificate, which we will also send you, and on top of that, we would like to also thank you. So we made a donation in your name for the IZTECH Foundation, which supports our students in their education. So we would also like to thank you for that.
Thank you. Thank you. It's my honor, and I appreciate it very much. It's I think what you're doing at IZTECH is excellent, and I'm really looking forward to seeing you all in person to discuss various things in the future. Thank you so much.
Thanks a lot. Also here. Yes, we can hear you loud and clear. Thank you very much. So let me introduce you. Dr. Fırat Yaşar is a postdoctoral fellow at NASA at the Jet Propulsion Laboratory, and he specializes in microelectronics, photonics, and optical systems. Now, more specifically, Fırat worked on X-ray imaging detectors and with single photon detectors, and he also works on quantum gravity gradiometers. And all of this, or at least half of this, he is doing in space. Well, at least his experiments are going on in space. Before he started at NASA, he was also working at IBM Global Foundries, where he developed silicon photonics packaging, and he worked with optoelectronic devices. There he also earned a couple of awards such as the Micro Device Laboratory Team Award and the Global Foundries Spotlight Award. So it's with great pleasure that I hereby will give the floor, or well, the mic in the camera, to Fırat Yaşar. Please welcome him.
Thank you so much for the introduction. I mean, I'm so pleased to be here. My name is Fırat Yaşar. Yes, I'm a postdoctoral fellow at Micro Device Laboratory of Jet Propulsion Laboratory of NASA. And I'm a member of Photonics and Quantum Sensors Group since 2021. Today I will be talking about microelectronics for space, and it will be specifically for photonics systems. But before I start, I would like to thank Professor Canan Varlıklı for having me here and coordinating this professional event. And it is also great to see photonic-related synergy in Turkey. I hope I could also contribute to the ongoing activities and increase awareness. So the outline of my talk today is going to be like, I will also briefly introduce myself, my background, and my research activities. Then I will highlight some of the research topics that I was involved in, like in my last couple of years. And one of them is gallium nitride photonic crystal fabrication for X-ray imaging detector applications. This is going to be for X-ray space telescopes like NuSTAR and Chandra. And the second one is going to be far-infrared membrane-based metasurface filters. This is bandpass filters specifically designed for deep space communication in far-infrared. Then I'll talk about the hybrid photonics packaging work that I was involved in IBM Global Foundries. And then finally, I will show you some sketches for the laser optic systems that we developed for cooling the atom to measure gravity gradients precisely. So I studied physics back in Turkey. I graduated in 2010. I studied in Anadolu University. I also joined METÜ for a master's degree for 2 years. After my master's degree in METÜ, I got a fellowship. I came to United States and I got my master's degree and PhD in University of Wisconsin-Madison, and I graduated in 2020. All of my academic endeavor was focused on photonics and optoelectronics, computational modeling, designing, metrology, fabrication, and characterization. And right about the pandemic, COVID was hitting the world, I joined IBM Global Foundries located in New York. So I was on the Silicon Photonics team of the Global Foundries, and we were developing packaging and hybrid integration solutions for other technological applications. After then, like in 2021, October, NASA extended me an offer, and there was really cutting-edge research projects that are going on. And I joined a Jet Propulsion Laboratory Micro Device Lab as a postdoctoral fellow, and I was a member of Photonics and Quantum Sensors Group in Micro Device Laboratory. The image on the back is like the researchers and scientists in the Micro Device Laboratory. And I'm the one that, I guess I'm the only one whose eyes are closed. So I'm here, but we have about 110 people, 7 different groups. We have class 10 and class 100 clean rooms downstairs, and we do advanced fabrication besides having optics lab, several optical tables for metrology and characterization. And this is a brief educational and employment history of myself. So let me start with the gallium nitride photonic crystal fabrication. So this is, again, X-ray imaging detector. This is the continuum of my grad school work when I was in the University of Wisconsin-Madison. I and my advisor were working on gallium nitride material for X-ray imaging detectors for medical imaging application when I was in grad school. And then after joining JPL, I converted the focus of this work for space applications rather than medical imaging. And we said that, okay, let's design an imaging detector with gallium nitrides, which will give us much better spatial resolution. And NASA also prioritized broadband X-ray detection. We said that, okay, let's focus on broadband X-ray detection with this gallium nitride photonic crystals. And the scintillation mechanism is already very fast, so it will be really good for ultra-fast imaging applications. And like there is a motto like called anything flexible, anything thin is flexible. So we said that as long as our layers are thin enough, we can make flexible scintillator detectors as well. And if the design is also focused on polarization-sensitive imaging, we can also achieve polarization-sensitive imaging with this detector architecture. So on the top image, like a state-of-the-art scintillators like gallium nitride, for example, if X-ray hits gallium nitride, what happens is gallium nitride softens the X-ray and emits a light at much lower energy or larger wavelength than the X-ray itself, which we call scintillation. And this emitted light goes towards the pixels, which is 2D, integrated on the back of the thin film layer of gallium nitride, which is the light blue color here. So these detectors has about 20 micron spatial resolution. And also there is a lot of crosstalks between the pixels since the emitted light goes towards the pixels uniformly. Also, like 2D pixels, if you have 1000 by 1000 means you have 1,000,000 pixel integrated to scintillator architecture, which is a lot of burden on the readout circuitry. And like since this is only limited to one layer, like gallium nitride, for example, the responsibility of gallium nitride in terms of scintillation emission once X-rays are emitted on, it is like from 0.1 kilo electrovolts up to 10 kilo electrovolts. So these are called soft X-rays. We said, okay, let's change this a little bit. And we find a solution that are currently considered as limitation. We said, okay, so let's first, instead of using like plain scintillator thin films, let's have like photonic crystals, which is like periodical cylindrical air holes here. And let's design this photonic crystals so that the scintillation light, instead of going vertically to the pixels, it goes towards the edges in a collimated way. And then we said that, okay, then after, if the scintillation light goes towards the edges rather than going to back panel, let's say, we said, let's put the pixels on the edge. And this will be fundamentally reducing the number of pixels because instead of 2D pixels, like for example, again, 1000 by 1000 is 1,000,000 pixel. But if you have a linear pixel array, can do the same type of imaging, that means 1000 and 1000 pixel, which is 2000. Still almost 1,000 times less than 1,000,000 pixel, which is a lot of improvement and easiness on the readout circuitry. Also, thanks to the thin film nature of this gallium nitride material that we use, so we can curve them. And for the space applications, like in galaxies, X-ray flux are really, really at minimal level. So there are mirrors being used to focus X-rays on this X-ray focal plane arrays. And those X-rays are coming at an angle. So if we are able to bend or curve this focal plane arrays and we can minimize the incidence angle, then we could also improve the optical coupling efficiency. So that was another niche that we wanted to introduce. And since we removed the back panel 2D pixels arrays from the back panel and putting them on the side, then we enable the vertical architecture of this imaging detector, which is very novel. I might be personal on this, but I think this is revolutionary because now we will be able to stack multiple detectors on top of each other and each of them with different functionality. Like, for example, the top layer might be specifically designed for spatial resolution, the second layer for energy resolving capability, and the bottom layer is for polarization sensitive imaging. And in this way, one architecture would be a solution to multiple problems, like a one band-aid, multiple scars kind of solution. And I mean, this will also introduce, you don't need to stick to like solo type of material, like it doesn't need to be necessarily gallium nitride every single layer. This could be like zinc oxide or barium fluoride on the alternative layers. And each material is sensitive and responsive for different X-ray regimes. So in this way, we can broaden the detection range. So this will come with broadband X-ray detection, which is prioritized for NASA. And like as we increase the vertical thickness, then we can stop more X-rays, and more X-rays means like a better resolution and better performance. Why polarization sensitive imaging is important for X-ray imaging detectors for space is, like, again, generally these detectors are being used to image black holes in the universe. And like we have no idea about what is inside the black holes, but we have an idea about what comes out of black holes. And those are X-rays. So if we can kind of initiate a polarization sensitive type of detection coming out of black holes, then we can get an idea about the orientation of the X-ray emissions coming out that can give us an idea about what is inside the black hole. So that's why these are very important parameters. I joined JPL in 2021. I wrote this proposal. We secured about $1 million for this, and it got into third year. So we got really interesting results. Those are really exciting. But we started with gallium nitride photonic crystals. We first obtained gallium nitride thin films with 5 micrometer thickness. And in the literature, one group in Japan, they were saying that, okay, once you hit gallium nitride, it will emit 550 nanometer light, which is shown in the inset image of this plot. And we said, okay, if that is the case, let's design our photonic crystal for 550 nanometer light emission. And let's introduce this photonic crystal so that it collimates the scintillated light towards the edges efficiently. Okay? So this requires a lot of photonics band gap engineering and a lot of dispersion surface analysis. After finding the correct structure and architecture, in our case, the radius of the cylindrical air holes are about or the diameter is about 138 nanometers, and the periodicity is 208 nanometers, which is really, really small for conventional microfabrication, nanofabrication techniques. But the design is very simple. It's square lattice. So our modeling includes ANSYS numerical FTTD simulations. And in this modeling result, you see that, okay, scintillated light will go towards the edges in this cross shape rather than going towards the edges uniformly like a water waves. So again, this comes to like advanced isofrequency contour analysis of the photonic band structure engineering of gallium nitrides, thanks to the photonic crystal. We also simulated how the light will come out toward, like within the edges of the thin film. So like towards the bottom of this plot, you see that light comes out everywhere. And once the pixels are integrated on the edge, there will be so many pixels integrated and interacting with the light simultaneously, which will introduce a lot of crosstalk. But then the top image is showing a perfect photonic crystal fabricated. And thanks to the photonic crystal on the top image, the light comes out in a confined way, and the light will be interacting with minimum number of pixels. Eventually, it will improve signal to noise ratio and improve the crosstalk of the pixels. So we did advanced computational analysis to see fabrication tolerances, what would happen if gallium nitride was not on sapphire, but there was silicon dioxide in between, how would be the light confinement would be, like those type of analysis we have done computationally before jumping into lab. Then once we get satisfactory results in modeling and we got into clean room, we said, okay, let's fabricate this. Again, once I said conventional lithography methods would not be sufficient to create this architecture, what I meant was like creating this cylindrical air holes with a diameter of 135 nanometer is not doable with like a conventional lithography, but you need to use E-beam lithography, in which the feature size are much smaller than a micron, which is our case here. But then E-beam lithography, yes, it is coming with higher resolution. You can create smaller features, but it's very expensive. It takes a lot of time and requires expertise, and it's not readily available everywhere. We had 2 different types of E-beam lithography in our clean room. We had such an experience like a fab team, and we developed a method with E-beam lithography, which we call dot-on-the-fly technique. And E-beam exposure was pretty much the size of these air holes. And instead of exposing 10,000 times for one air hole, we exposed one like a stamp and move to the next one and move to the next one. So that's a dot-on-the-fly technique that we developed. Actually, we didn't develop this. Let me take my words back. We used this technique, and thanks to this technique, we reduced the manufacturing of this photonic crystal pattern on 4 inches wafer, we reduced the time from almost a month to slightly less than a day. This is a big improvement in terms of fabrication of these features on gallium nitride material. For the people who has experience in gallium nitride processing, nitrides are generally hard to deal with, but gallium nitride is extremely hard material. So we had to develop triple hard mask layers. Again, the conventional photoresist wouldn't work to etch this deep, like 5 micron hole with about like 138 nanometers diameter. This was really hard. That's why we had to develop triple hard mask layers. And eventually we achieved high aspect ratio etching of 1 to 30. And we published this paper in the Ekim Society this year. We also patented the method that we developed with the start-on-the-fly technique with the combination of triple hard mask layers. Then once we have the photonic crystal fabricated, the next thing was characterization. So we collaborated with the group that initially showing that, okay, this guy will scintillate at 550 nanometer. We said, okay, now we have a photonic crystal gallium nitride. Can you please characterize this for us? Let's make a collaboration. And we started collaborating with 2 research groups at Nara Institute of Science and Technology in Japan. They have such an advanced radiation sources like UV, X-ray, and alpha particles that is compatible for thin film scintillator characterization. And we asked them to characterize our photonic crystals. And they did such an amazing job, very timely, and they measured all of this for us at different orientations. For us, the most important thing was once radiation is hitting the photonic crystal, measurement on the edge was very important for us because the way that we wanted to change the current state of art was removing the back panel 2D pixels, taking them from the back panel and putting them on the edge, right? So then this measurement was carrying a lot of importance. So here in this plot, you see like a red color and black colored lines. So black color means there is no photonic crystal, plain gallium nitride thin film. And once you hit it with X-rays, there is a sideband emission around 400, 300 in that region. That's very common for gallium nitride. Also, sideband emission in around 600 or above. That's very natural. But thanks to the photonic crystal that we introduced, which was specifically designed for 550 nanometer, it would only collimate and guide the light towards the edges as long as it is 550 nanometer. So basically, the detection on the edge, what we are reading, these are normalized graphs, by the way. So we have more 550 nanometer light on the edge compared to plain gallium nitride. So this ended up saying that, okay, we had really good filtering of sideband emission besides spectral proof of collimation of 550 nanometer light. We also hit it with the UV source and with plain gallium nitride thin films and with photonic crystal gallium nitride thin films, we had the comparison and we realized that we have almost 3 times more light comes out at 550 once the UV is hitting the gallium nitride. So that's also a fundamental improvement in the quantum yield. We submitted this paper to Advanced Photonic Research. It is accepted and it will be published. It will be published in the upcoming days. So for this work, again, we have a lot of work to do. So we are still working on spatial proof of the self-collimation. I developed a setup. This is like with advanced micro-positioners, fiber in, fiber out type of setup. I will locate the gallium nitride thin film here, and we will focus 550 nanometer light to the edge like a wave-wide coupling measurement. We will also have a fiber out measurement on the other side, and we will sweep the fiber from one edge towards the other edge to see the beam profile spatially. Based on our simulation results, we should be able to minimize and confine the light below micron level. That means the spatial resolution will be reduced from about 20 micron to sub-micron levels. This is also a big breakthrough for X-ray imaging detectors. We also stack multiple gallium nitride photonic crystal thin films on top of each other. This is the first time in the world people are putting gallium nitride photonic crystal stacks on top of each other. We also start getting really good light yield out of this, both on the back and the edge measurements. The next is integrating linear detectors on the edge rather than a fiber to see how it will interact with the originally proposed linear detector integration architecture. And we also start doing this, and we get really meaningful results in terms of scintillation light coming and hitting this detector. And now we are working on readout circuit development with this linear detector integration and gallium nitride photonic crystal with Philip chip bonding method of gallium nitride with pixels on the edge and the silicon fan-out design for wire bonding. So these are the ongoing activities with X-ray imaging detector work. Again, this got into third year, and we are getting really exciting results. And I believe this will change the way that X-ray imaging detector work in the near future. So next topic that I'm going to introduce is the far-infrared membrane-based metasurface filter. Again, this is the filter work that is designed for deep space optical communication and in far-infrared domain. In this work, compared to X-ray imaging detector, this was with a really minimum amount of funding. This was about a $50,000 budget. Very limited, very small team, but I did the design, modeling, and optimization of these metasurfaces besides fabrication and metrology. I also worked with a couple of grad students in Caltech. So what we did was, Far Infrared Astronomy Society, they were in need of a lot of bandpass filters at different far infrared domain, including 15 micrometer, 20 micrometer, 30 micrometer. So we sat down and we designed, again, with HFSS and FTTD simulation. We said, okay, if there is a big need for bandpass filters, let's at least computational design some good bandpass feature filters, and we have the design ready. And whenever someone else comes us and says, okay, I need the filter, and we will have the design ready, and we are going to go downstairs, get in the lab, fabricate it, and give it to them for their measurements to see whether there is any improvement or not, right? So what we did was we designed several bandpass filters, which are shown. These are computational results of the bandpass filters that we designed. And we said that, okay, whoever is going to come, we are going to give them a design and we'll fabricate it. Again, our target is far infrared domain, and these are going to be bandpass filters. It will pass some specific wavelengths, but reflect all other wavelengths that are not wanted. The design is like this. Polyimide material is the fundamental material of the Kapton tape. I believe all of you, or almost all of you, have been using a Kapton tape in the lab. So polyimide is the fundamental ingredient of it. So we start using thin film coating of polyimide, introducing a gold thin film in between another polyimide, another gold thin film and polyimide. This is like a sandwich architecture. So this gives us a vertical thickness control. So in Z-axis, we have a control over the thickness, which is important for optical refraction, transmission and reflection. Also spatially, the feature that is repeated, which we call photonic, here is the cross mark in the literature. People were designing this type of mesh filters with repeated cross filters. We also did the same thing, but we designed it again for different wavelengths, and all are identical, all cross shapes. So basically, not only vertically, but also spatially, we have a control over the photonic architecture. That means we have a 3D photonic architecture that we have liberty. So we optimized the geometric features and lattice parameters and everything. Again, the materials that we used is a polyimide and gold. And on the right side, like this is the representation of the substrate that we use. It's like a silicon dioxide sandwich silicon. I apologize, sorry. And like we start with like a thin film deposition of polyimide gold, polyimide gold, polyimide. Of course, we pattern the gold layers in between. So then once we deposited all of these features on the right side, we flip it upside down and back edge the wafers so that we only have polyimide layers and gold layers, but no more silicon dioxide and silicon. So again, the polyimide thickness that is targeted was about 2.2, and the deposited like with a pattern gold thin film was about 100 nanometer. And you can increase the layers as much as possible, as many as possible, and this will also improve the bandwidth of the bandpass filters. So we did this design and fabrication in our lab. Here is the SEM image of the like a fabricated pattern. The edges at the first batch was not as like sharp as we wanted, but we also simulated this to see how would it impact the results. But what we achieved here was first, for all of the bands that I introduced, we had a bandpass filter in like 16 millimeter by 14 millimeter geometry, which is compact, like a snap-on type of filter. The detector group were able to use this without damaging their detector architecture, and they were these were very strong, and again, no damage on the detector architecture. And we had one variety of designs on one wafer. So basically, one fabrication process was giving us multiple filters on the wafer rather than having different fabrication for different filters, which is a lot of work. So this was a success. Here are the simulation results and the experimental FTIR results of the filters that we did. So also, luckily, our experimental and simulation results were well aligned. They were matching each other. That was quite impressive. We also had 80% transmission efficiency. Everyone was happy. So we did a lot of fabrication tolerance investigation here too. And so, I mean, we also submitted this paper to Optics Express, and it is accepted with minor reviews. We are going to change a couple of things and resubmit it. Hopefully, it will come out really soon. For this work, some of the future activities is there are other polymer materials than polyimide with better transmission efficiency than 80%. This is right now I'm writing proposals for this to secure more funding and to do more advanced bandpass filters. Also, there are some other methods that we can expand the detect, like a filtering range, taking it below 10 micron, taking it also above 100 micron, which will keep more people happy. But this is basically the brief introduction of our far-infrared bandpass filter. So now I'm going to introduce hybrid photonics packaging work that I did at IBM Global Foundries. So after grad school, as I mentioned earlier, like I joined as a technology and development engineer at IBM and Global Foundries. That's a fab, a semiconductor fab, cooperated by IBM and Global Foundries. And we were about 10,000 engineers and scientists working in the lab. It's really big. It was like the biggest foundry, US-based foundry. It's competitor to TSMC. There is a lot of employment opportunities, and photonics is hot topics. They are looking for talented people, and the pay is really good. I was on the silicon photonics team, and my specific focus was hybrid integration technologies and processes for like lasers on chip, waveguides on chip, detectors on chip, those type of technology development. I was involved. And the instrumentation that we had was also cutting edge, very expensive tools. I don't think it would be available everywhere. So that was also enabling us to do really cutting edge stuff. But the laser integration process that I was developing was with a tool enabling me to like precisely integrate a semiconductor laser on chip with about 100 nanometer resolution. And one laser integration was taking about 20 to 30 seconds. Since this was foundry level silicon photonics packaging rather than R&D, like one of our focus was also scaling up the integration. Rather than having one successful integration, we wanted to scale this up by coming up with processes that are simple, repeatable, like problem-free, and efficient. So that we had to develop compact solutions for this type of processes with efficient coupling, less than 2 dB loss. So here is the laser on the left image. You are seeing laser. A tool was, again, artificial intelligence using image recognition tool. We were teaching the tool to recognize the laser and the physical cavity where the laser will sit. And tool was going, picking the laser and deciding which cavity it's going to sit. And locating the laser with really, really high precision. And with a laser soldering technique on the back of the wafer, it was soldering the lasers on chip. And since the laser soldering, the diameter was about 1 millimeter, so population density of the semiconductor lasers that we could put on chip was very high. So we can put like hundreds of lasers right next to each other with about 3 or 5 millimeter gap without damaging alignment on the other one. So not only laser integration was my responsibility, but also we were having like V-groove designs, and I was also precisely integrating fibers on the back so that we can have a complete laser optics module to be measured. Okay. So, and on the right image here, you're seeing the physical cavity with metallization here, 2 metal pads. And these metal pads were not requiring any more wire bonding of the lasers on the top, which damages the laser. Here is the laser mode profile and the taper architecture. This is another image, SEM image. And this is infrared image when the laser light is on. So laser is like guided, emitting the light, and it goes into this waveguide here. I also worked on a lot of optical adhesive materials to fill in between the laser and the waveguide here so that we can minimize the losses in between this area. Yeah. Also, besides developing processes, I worked on reliability. That's also a very new area for photonics, especially for space applications. Depending on application, reliability is different, but for space, it is so different. Like we had to consider radiation as a reliability concern, or also vacuum, temperature cycling, vibration, shock absorbance, and everything. So when I was in Global Foundries, space was not the main motivation, but it was the telecommunication. But I was still mechanically and temperature-wise, I was checking how strong the integration is. So again, as I told you, thanks to the physical cavity design that we introduced, it was not requiring any of the wire bonding on the top, but our metallization was only at the bottom. This was minimizing the time that the laser is being integrated and also almost eliminating the damage on the laser. So I also did a lot of metal alloy investigation. It was not my strong suit, but I learned a lot. Gold and tin alloy was the one that we were using. A lot of parameters to consider: the design, thickness, the material selection, the compositional analysis, how much pressure we use on the semiconductor lasers, and what was the band temperature, how long was the bonding. They were all the parameters that we were taking into account and using as an optimization parameter. So yeah, I did a lot of also AFM measurement on this lasers integrated. Although the laser, the metallization that we introduced was so novel and so efficient, it was still kind of causing bulbs on the semiconductor lasers, eventually causing misalignment on the light from the laser to the waveguide. So this was also another concern that we were taking into account and trying to optimize. I put together a lot of test setups there to speed up the measurements and minimize the insertion loss. And I did a lot of root cause analysis. Actually, this was the work that taking me from IBM to NASA. So the next topic that I will introduce, and this will be the last topic that I will introduce, I will try to keep it short. But again, JPL, NASA wanted me to maintain my packaging type of experience that I developed at IBM, but used at NASA for laser optic systems development for quantum gravity gradiometer. This topic I cannot show you much because it's still going on, but I worked on this project as like a systems level. Let me give you a brief introduction. So we are trying to develop a laser optic systems with a physics team that is called Cold Atom team in JPL. So there are two teams, photonics team trying to develop a laser optic setup, and physics team trying to use that setup to cool the atoms. So cooling the atoms is like some fundamental physics, like it's like Zeeman effect of light and matter interaction. But basically, like we were using laser light to trap the atoms into a teeny tiny area by giving them pulses in every direction. We were using 6 different lasers in positive X, negative X direction, positive, negative Y, positive, negative Z, and giving them pulses in a synchronized way so that we can trap the atoms in a capsule. Basically, like if you are minimizing the vibrational movement of atoms, it means that you are cooling the atoms. Or if the atoms are hot, the vibration is really big. Or if you trap them, they are cool. They are cold atoms. So 2 teams working on cooling atoms. So how it's going to be useful is like cooling atoms will be used for measuring gravity measurements, being used in gravity measurements. And the way that gravity measurement is done is like, okay, you have cold atoms, you know the precise location of them. And at a single point on a surface, you release the atoms, and at 2 time checkpoint, you measure the time that those atoms fall down, and that time will give you an information to back calculate the gravity. Then you keep these measurements at another point. Basically, an airborne systems, it might be a balloon, it might be a drone, it might be another air vehicle, or it might be a Mars rover carrying this instrument and making measurements on the Mars surface at every single point, measuring the gravity with high precision. And at the end of the day, it comes back with a lot of data, spatial data of gravity, and we measure how gravity changes, and we relate that information with the underground structure, whether there is petroleum, water, ice, minerals, or other elements. So that's how it's being used. So laser optic system was very critical. Current state of the art was using a laser optic setup that is really big, really chunky. This is a killer for space applications. You gotta have something really compact, lightweight, really reliable. Again, they were using a laser optic system that is not compact, but using rubidium atoms for cooling. And rubidium atoms resonation wavelength is about 784 nanometers. And the laser optic setup that when I was being used was designed for 784. But there were limitations on that. Then we switched to cesium atoms from rubidium, in which the operational wavelength is 852, not 784 anymore. And when we take this project, like the team was able to cool about 10 to the 6 atoms, like a million atoms, and they can cool it down to microkelvin temperature. That is when we took it over. Like a million atom and microkelvin temperature. That's where they were reaching it. Our target was cooling 100 million atom and not microkelvin, but pushing the cooling temperature to nanokelvins. That was our target. And based on our simulations and modeling, we were able to do that with cesium atoms. But again, this was all depending on this optical photonic architecture, how efficient it is working, how much light we could carry through this fiber optic setup. It was very important. The higher the power, the more atom you cool to the cooler temperature. So our setup was, this is not the full architecture, but just a summary. Like we had about like 65 photonics and optics component, like doing this atom cooling. And we were having a cooling laser, amplifiers, then we were splitting the light, attenuators, MEMS switches. Like these are all individual fiber optic components that I obtained them, assessed them individually, component-wise. I put them together and I get them up and running. I also synchronized them. I also did some reliability measurements on these MEMS switches because they were not functioning properly. But we were able to carry about 25 milliwatts of power for each mode here that enables us to cool the atoms. We were successful. Yes, we reached our target, but the system was still not compact enough. So again, JPL wanted to leverage my packaging experience. So they wanted to put these photonic components rather than having them individually. We wanted to put a laser on chip, splitter on chip, attenuator on chip, switch on chip. So there was a common expression of my manager said, "Oh, why don't we put everything on a credit card size area?" At this moment, it's not possible. But having really hybrid solution, really small, compact solution, advanced photonics packaging was very critical. But also, these tools and instrumentations are really hard to find. Packaging, for that reason, at R&D level is so hard. So you gotta outsource it. You need to find experienced people with proper high precision instrumentations and so on. But at R&D level, again, we were able to come up with a smaller breadboard architecture carrying all of this optical setup, and we were successful delivering it to Cold Atom Lab, and they were also successful for cooling the atoms. So, yeah, this was, again, I'm so sorry that I couldn't show much details because this is still an ongoing activity, but I wanted to at least show the overall architecture. This will be a breakthrough for in the upcoming years for undergrad structure investigation. So these are my slides. Thank you so much for listening. Now, floor is open to you, and if you have any questions, please feel free to ask.
So thank you very much, Fırat. So if there are any questions, yes.
Thank you so much for the nice lecture. I just wanted to maybe know some details on how technically these gravitational measurements are taken. So after atoms are cooled, what is happening next?
Once we cool the atoms to those temperatures, is your question like what happens next?
Yep. Okay,
so assume that there are two checkpoints, okay? Point A and point B, and atoms are gonna free fall, okay? To get like a precise measurements of this timing of the free fall, you gotta precisely know the location of the atoms. If there is any ambiguity or any uncertainty of the location of the atoms, that also reflects to the uncertainty in the timing measurements. And eventually, it reflects to the measurement of precise gravity measurements. So what happens once we cool the atoms is we precisely know the location of the atoms, we let them free fall, and we measure how much time it takes from point A to point B for those atoms to free fall. So we let them free fall, and we measure the time, and we relate it to the gravity that is exposed on the atoms. And again, this doesn't necessarily need to be for this planet, but for Mars, for Moon, or for any planets that we have no idea, with an airborne system that can be used for gravity measurements.
Thank you.
Yep.
No other questions? All right, then I will ask maybe one more question, if I may. In your first topic on the X-ray detectors, you said like, okay, we just measure, we gonna detect from the side, so you have a whole line of pixels that you're detecting, and how are you untangling all these pixels? So you're
the measurements. Okay, so let me maybe if I go back to my slides, I guess. Okay. So these measurements, for example, we made it with a fiber, so without any detector integration. So, and this was on the edge, and we were able to see the emission on the edge. We also integrated this, that photonic crystal in this image with the linear detector. This is commercially available. This is not in-house, by the way. In-house one is the one that we are working on right now. But these are Hamamatsu line detectors with about 2,000 pixels along this line, maybe some more. I don't remember exactly. And with epoxy and glue, with optical refractive index matching material, we fix the gallium nitride after meticulously cleaving the photonic crystal and coupling it, fixing the position, and epoxy UV curing so that the position is fixed. Then we let it get it exposed to radiation and do the measurements on this detector architecture. So again, integration is hard contact. Basically, we cleave this photonic crystal very smoothly, and we let it physically touch the detector. It's a hard touch. Even we put some pressure, and we apply epoxy UV with different refractive index matching material again, fix the position, and do the measurements. So with this detector, we were also able to do measurements, but light that is coming out of photonic crystal was so dim for this detector because this didn't have internal gain.
Yeah, thank you very much.
Yeah, you're welcome.
Maybe one general question, maybe for the students. If you were a student again, where would you go, GPL or IBM Foundries for your first job or your?
None of them. I would rather coming back to Turkey and working in Turkey with the universities in my home country with my people, because like space technology, like semiconductors, the big industry, it is like agriculture. Like I believe everyone has chips via their phones or tablets or something. So I believe it will be really critical for any country to develop semiconductor technologies, photonics, optics, and I would rather working in Turkey with the universities, but now opportunities are more available here. That's why I'm here. But I would rather being in Turkey. If that's not the option, definitely NASA is a great space, is a great motivation. Even thinking about anything that we touch have a potential to go to space is really motivating. Like this X-ray imaging detector, for example, it's a really strong candidate. I own like 3 patents on that right now, and the activity is growing really big. If it is successful in 40 to 50 years after passing reliability tests, it will fly. If it is successful. That is so motivating. I mean, as a person who started in Turkey, like move over ocean, come to US, get a PhD, and now working on something that has really potential, that's very inspirational, to be honest. But on the other side, NASA pays really poorly. we are government employees. We have like I could make a lot of money if I go to industry. Those are the downsides. But again, science is the most important thing here, and it's very inspirational work. And the people that we work with is also, they are really amazing people.
Thanks a lot for sharing this. We would like to share, nope, sorry. All right, yes. So we would like to share this certificate of appreciation for you, and as well as a certificate which is given to you for making a spontaneous donation to the IZTECH Foundation that will support our students. So. So thank you very much, and thank you for the great talk and inspiration to our students and a little bit older students like me.
Yeah, we are all students. Again, I would like to thank you for giving me this opportunity. I hope I could increase some awareness, but people can find me on LinkedIn, and if they think I can be helpful with anything, just don't hesitate to reach me out. Maybe we can do something together in collaborations and so on. Again, thank you so much for this opportunity. It was a great pleasure.
Thank you very much.
Thank you.
See you next time. Yes. It's a very good point. So this session has ended. So please see you all tomorrow.